On August 15, 1977, a sophisticated radio observatory in Ohio intercepted an extraordinarily potent transmission originating from the furthest reaches of the cosmos. For a duration of 72 seconds, an entity in the vast expanse directed an intense signal toward us, employing the precise radio frequency that would be theoretically utilized for interstellar communication. The astronomer who identified this phenomenon was so astonished that his only annotation on the data readout was a single word: wow. For a protracted period of 48 years, the origin of this signal remained an enigma until the recent revelations of yesterday. An astrophysicist from Harvard University, Dr. Avi Loeb, has published intricate calculations that are profoundly disquieting. On that very day in August 1977, an object was positioned approximately 600 astronomical units away, with its trajectory directly aimed at Earth. This object is currently traversing our solar system at an astonishing velocity of 60 kilometers per second. We have designated this entity as oumuamua, and its dimensions exceed that of the island of Manhattan. The mathematical evidence is irrefutable. The statistical probability that this alignment is merely a coincidence stands at a mere 0.66%. This implies a 99.4% likelihood that oumuamua was the source of that signal. However, the situation escalates to a truly unnerving degree. This celestial body is exhibiting characteristics entirely dissimilar to any known comet. It is releasing pure nickel, conspicuously devoid of iron, a composition exclusively observed in industrial manufacturing processes. Furthermore, it possesses what appear to be illuminating elements directed forward, rather than the expected trailing tail. Its orientation is perfectly aligned to facilitate close passes with Mars, Venus, and Jupiter. And in 29 days, specifically on October 29th, it is predicted to vanish behind the Sun, obscuring its subsequent actions from our observation. The scientific community is experiencing significant internal conflict over these findings. NASA maintains that oumuamua is simply a comet, yet they are unable to account for the presence of nickel. They cannot explain its peculiar trajectory. Crucially, they cannot rationalize why it would have announced its presence with a transmission equivalent to that of a nuclear reactor 48 years ago. Time is of the essence. We have less than a month before oumuamua disappears from our observable view. And if Dr. Loeb's projections regarding its future conduct prove accurate, the implications will fundamentally alter our understanding of everything. This is the narrative that certain entities wish to suppress. If this revelation resonates with you as profoundly as it has with me, please engage with the content by liking the video and subscribing to the channel as we embark on an in-depth exploration. In the comments section, kindly share your geographical location, the current time in your region, and the most peculiar incident you have ever experienced. Chapter 1. The Signal from Oumuamua. Unraveling the 48-Year Mystery. Allow me to meticulously guide you through Dr. Avi Loeb's groundbreaking discoveries. Because once you comprehend the numerical data and grasp the geometrical significance of the events that transpired in 1977, you will inevitably conclude that we are not dealing with a mere cosmic anomaly. We are confronting something that defies every established probabilistic model. September 29, 2025. This is the date when Dr. Loeb disseminated his findings. The precise timing is critical, as oumuamua is rapidly approaching. What he elucidated in that academic paper establishes a profound connection between two of the most perplexing phenomena in astronomical history. The WOW signal and this interstellar visitor are not separate enigmas. They are, in fact, manifestations of the same mystery, separated by a span of 48 years and an astronomical distance measured in hundreds of billions of kilometers. Let us now revisit the observations made by Jerry Emin on that fateful night in August. The Big Ear radio telescope, operated by Ohio State University, was engaged in its routine celestial survey, diligently analyzing cosmic radiation for discernible patterns. At precisely 10:23 p.m. Eastern Time, the telescope acquired a lock on an unusual signal emanating from the constellation Sagittarius. The intensity of the signal experienced a dramatic surge, not a marginal increase, but a colossal spike. The onboard computer registered this as 6EQUJ5, a designation signifying that the signal strength was 30 times greater than the ambient cosmic background noise. Emin meticulously reviewed the printed data several days later. Upon observing these numerical values, he retrieved a red pen and circled them. Adjacent to this sequence, he inscribed the word WOW, accompanied by an exclamation point. This marginal note subsequently became the designation for the phenomenon, the WOW signal. For almost 5 decades, its origin remained an inexplicable enigma. The signal persisted for precisely 72 seconds. This duration is not arbitrary, It corresponds to the time required for Earth's rotation to sweep a stationary point in the sky across the observational field of the Big Ear telescope. Whatever entity transmitted that signal was not in motion. It was stationary at a specific celestial locus, broadcasting at a frequency of 1420 MHz. This frequency corresponds to that of neutral hydrogen, the most abundant element in the universe. If one were endeavoring to transmit a signal that any intelligent civilization would recognize as artificial, this particular frequency would be the logical choice. It represents a universal communication protocol. However, the crucial factor rendering it inexplicable was its non-recurrence. Every available telescope was directed back towards that precise region in Sagittarius. The result was silence. For 48 years, astronomers have continued to monitor that location, consistently finding nothing. It was as if an entity in the cosmos had offered a singular salutation and then ceased all communication indefinitely, until Dr. Avi Loeb performed his calculations. Dr. Loeb is not an outlier in the scientific community. He holds the prestigious Frank B. Baird, Jr. Professorship of Science at Harvard University, having previously chaired the Department of Astronomy and the Board on Physics and Astronomy of the National Academies. His academic contributions include the publication of over 900 scholarly articles. He is not a purveyor of conspiracy theories operating from an obscure location. He represents established astronomical scholarship, or at least he did until he began posing questions that made his colleagues uncomfortable. The question he posed concerning oumuamua was straightforward. Where was this object situated in August of 1977? Oumuamua follows a hyperbolic trajectory, indicating that it is not gravitationally bound to our Sun. It originated from interstellar space, is currently transiting our solar system, and will depart, never to return. Due to the nature of its hyperbolic orbit, its position can be determined with extraordinary precision at any point in time, past or future. The mathematics involved are precise. The gravitational equations are unequivocal. Dr. Loeb traced the object's orbit backward in time. On August 15, 1977, oumuamua was located approximately 600 astronomical units from Earth. An astronomical unit is defined as the distance between the Earth and the Sun, which is approximately 150 million kilometers. Therefore, 600 astronomical units represent a distance 600 times that magnitude. It was situated far within the outer reaches of the solar system, traversing the darkness beyond the orbits of Neptune and Pluto, within that immense void where sunlight appears as merely another star. However, the distance itself is not the most startling revelation. The truly astonishing aspect is its direction. The WOW signal originated from celestial coordinates corresponding to a right ascension of 19 hours and 25 minutes, which translates to 291 degrees and a declination of 27 degrees. These values pinpoint a specific direction in space, analogous to latitude and longitude, but applied to the celestial sphere. On August 12, 1977, 3 days prior to the detection of the WOW signal, oumuamua was located at a right ascension of 19 hours and 40 minutes, equating to 295 degrees and a declination of 19 degrees. Allow this information to fully register. The signal emanated from 291 degrees right ascension minus 27 degrees declination. Oumuamua was situated at 295 degrees right ascension minus 19 degrees declination. This represents a separation of approximately 4 degrees in right ascension and 8 degrees in declination. On the vast canvas of the entire sky, which spans 360 degrees circumferentially and 180 degrees from pole to pole, this alignment is negligible. We are discussing a scenario where the signal's origin and the object's location are separated by less than 10 degrees within a celestial sphere encompassing tens of thousands of square degrees. Dr. Loeb calculated the probability of such an alignment. If one were to randomly select two directions in the sky, what would be the likelihood that they would be aligned within such a narrow margin? The answer is 0.6%, which translates to less than a 1 in 160 chance. Put another way, there is a 99.4% probability that this is not a mere coincidence. Consider the implications of this statistic. An interstellar object, having traversed the galaxy for millions or even billions of years, coincidentally arrives within a few degrees of the precise location from which humanity detected its only confirmed candidate for an extraterrestrial signal. Furthermore, it was present at that exact moment the signal was transmitted. Dr. Loeb's investigation did not conclude at this point. He sought to ascertain the nature of the transmitter capable of generating the WOW signal from a distance of 600 astronomical units. The detected intensity of the WOW signal ranged from 54 to 212 Jansky. A Jansky is a unit of spectral flux density employed in radio astronomy. At a distance of 600 astronomical units, to achieve such an intensity at Earth, the source would require a power output of between 0.5 and 2 gigawatts. 2 gigawatts is equivalent to the output of a large nuclear power plant, exceeding the power generated by the Hoover Dam. This energy was beamed at a highly specific frequency, the hydrogen line, and directed towards Earth with remarkable precision. Natural astrophysical sources do not exhibit such behavior. Pulsars emit across a broad spectrum of frequencies. Quasars and magnetars operate similarly. Natural radio sources are inherently chaotic and broadband. The WOW signal, conversely, was narrowband, coherent, and precisely targeted, bearing all the unmistakable characteristics of an artificial transmission. We now have an indication of its origin, or at least of its location at the time of transmission. The signal also exhibited a blue shift of approximately 10 kilometers per second. Blue shift signifies that the source was moving towards us. The Doppler effect causes light and radio waves to shift towards shorter wavelengths when the source is approaching. The blue shift observed in the WOW signal was consistent with an object approaching at a velocity of 10 kilometers per second. Oumuamua is currently approaching the Sun at a speed of approximately 60 kilometers per second. While the blue shift is not identical, it falls within the same general range, the same order of magnitude. Dr. Loeb acknowledges this discrepancy in his paper, noting that while the velocities are not precisely the same, they are sufficiently consistent to preclude ruling out a connection. Therefore, we are presented with the following scenario. An object, having journeyed through interstellar space for eons, arrives in the outer solar system during the 1970s and transmits a powerful, narrowband signal at the hydrogen frequency, directed at Earth. Subsequently, it falls silent. For 48 years, it continues its inward trajectory, deeper into the solar system, undetected by our telescopes due to its remoteness and faintness. This continues until July 1, 2025, when the Atlas survey in Chile identifies a rapidly moving object, realizing it is not orbiting the Sun, but rather passing through it. Upon tracing its origin, it is determined to have originated from Sagittarius, the same celestial region from which the WOW signal emanated. Each additional piece of evidence renders the coincidence increasingly improbable. The trajectory originating from the same region, the precise timing, the blue shift, the power requirements consistent with an artificial source, and the remarkable alignment. Each of these elements, taken in isolation, might be dismissed. However, when considered collectively, they present a formidable challenge to Dr. Loeb's critics. This is a situation that cannot be explained away with vague assertions. One cannot simply label it a comet and expect the questions to cease. The mathematical data is publicly accessible. The orbital parameters are publicly available. Anyone can verify these calculations, and upon doing so, they arrive at the same conclusion. Either this represents the most extraordinary coincidence in the annals of astronomy, or oumuamua deliberately announced its presence to us in 1977, and we are only now deciphering the message. But if this is not a coincidence, if this object truly transmitted that signal, then we must confront the next logical question. Why? Why announce oneself and then cease communication? Why broadcast once and never again? What is the purpose of a greeting that is never followed up? Unless, of course, the signal was not a greeting at all, but rather something else, a beacon, a warning, a test to gauge our attentiveness. Or perhaps the signal was never intended for us in the first place. It is conceivable that we simply happened to be situated along the path of a transmission directed at something else, something closer, something already present within our solar system. This particular thought should evoke a profound sense of unease. Because if oumuamua was engaged in communication with another entity, it implies that it is not alone. And if it is not alone, then the fundamental question shifts entirely. We cease to inquire whether we are being visited and begin to ask how long they have been present, observing, awaiting, operating within the unseen spaces beyond our awareness. Chapter 2. 5 Improbable Anomalies that Undeniably Indicate Artificiality. It is imperative that we comprehend the current behavior of oumuamua, as its actions deviate significantly from the norm. It is not behaving like a comet. It is not behaving like an asteroid. It is exhibiting characteristics unlike anything we have previously encountered. And the more closely we examine it, the more perplexing it becomes. 5 anomalies, as identified by Dr. Loeb. 5 distinct attributes that, individually, are statistically improbable. When considered together, they represent a statistically impossible confluence for a random, natural object. In scientific discourse, anomalies refer to deviations from expected behavior, as predicted by our current models and observational data. Investigating one anomaly prompts further inquiry. 2 anomalies initiate a process of questioning. 5 anomalies, however, necessitate either a radical revision of our scientific frameworks or an admission that our existing models are fundamentally incomplete. Anomaly number 1, the trajectory. Oumuamua is on a retrograde orbit, meaning it is moving in the opposite direction to the orbital paths of the planets around the Sun. The majority of objects within the solar system orbit in the same direction, a consequence of their formation from a common rotating disk of gas and dust. Retrograde orbits are uncommon but not entirely unprecedented. Comets originating from the Oort cloud can approach from any angle. Therefore, a retrograde orbit in isolation is not inherently astonishing. What is truly remarkable is the extreme precision with which this retrograde orbit aligns with the ecliptic plane. The ecliptic plane represents the flat disk within which the planets traverse their orbits. Earth, Mars, Venus, Jupiter, Saturn, all of them orbit within a few degrees of this same plane. It functions as a cosmic racetrack, with all participants adhering to their designated lanes. Oumuamua is moving in reverse along this racetrack, yet it remains remarkably within its lane. Its orbital inclination, the angle between its orbital path and the ecliptic plane, is a mere 5 degrees. A 5-degree inclination for an object originating from interstellar space is astonishingly precise. If interstellar objects arrive from random directions, one would anticipate their trajectories to intersect the ecliptic plane at various angles. Most of the celestial sphere is not aligned with the ecliptic. The probability of a random interstellar trajectory aligning with the ecliptic plane within a 5-degree margin is approximately 1 in 500. We are already venturing into the realm of the improbable. Anomaly number 2, the timing. Oumuamua is not only aligned with the ecliptic, but is also arriving at a juncture where it will pass in close proximity to multiple planets. In astronomical terms, close proximity signifies within tens of millions of kilometers. On October 3, 2025, mere days from now, Oumuamua will pass within 29 million kilometers of Mars. This is considered a close approach, sufficiently near for the cameras on spacecraft orbiting Mars to capture detailed imagery. However, Mars is not the sole celestial body with which it will have a near encounter. Its trajectory also brings Oumuamua in close proximity to Venus and Jupiter. These encounters will not occur simultaneously, as the planets are distributed along their respective orbits. Nevertheless, the orbital path of Oumuamua is configured such that it crosses near the orbital paths of all 3 planets. If one were to randomize the precise moment of Oumuamua's entry into the solar system, while maintaining its trajectory, the probability that it would pass as close as it does to Mars, Venus, and Jupiter is approximately 1 in 20,000. Now we are accumulating improbable events. 1 in 500 for the trajectory alignment, and 1 in 20,000 for the timing of its arrival. Multiplying these probabilities together brings us to an estimated 1 in 10 million odds that this is a random occurrence. However, our analysis is not yet complete. Anomaly number 3, the vanishing act. Oumuamua will reach perihelion, its closest point to the Sun, on October 29, 2025. Perihelion is typically the most dynamic phase for a comet, as the solar heating causes it to expel gas and dust, creating a spectacular display. For Oumuamua, perihelion will occur at a distance of approximately 1.4 astronomical units, just inside the orbit of Mars. This proximity would typically allow for detailed observation. However, we will be unable to observe it because, on October 29, Oumuamua will be positioned on the opposite side of the Sun from Earth. The Sun will directly intervene between us and the object. Our line of sight will be obstructed for several weeks surrounding its perihelion. Oumuamua will be concealed from every telescope on Earth and every spacecraft in the inner solar system. This presents an ideal opportunity for clandestine maneuvers. If an interstellar spacecraft were seeking to alter its trajectory without detection, perihelion would be the opportune moment. A propulsive burn at perihelion, leveraging the Sun's gravitational pull to augment thrust in a maneuver known as a solar assist, represents the most efficient method of velocity modification. This yields a greater change in speed for a given amount of fuel, as the engines are engaged deep within the Sun's gravitational well. If Oumuamua maneuvers behind the Sun, we will not be aware of any alterations to its course until it reemerges in December. By that time, if its trajectory has changed, it could be heading in any direction. This timing appears deliberate. An object that has traveled for millions of years suddenly times its closest approach to the Sun to coincide with a period of complete solar occlusion. While it could be a coincidence, it is also plausible that it was meticulously planned. Anomaly number 4, the anti-tail. Comets are known for their tails. The tail invariably points away from the Sun, propelled by the solar wind and radiation pressure, which push gas and dust outward. The tail always trails the comet, resembling a windsock in a cosmic breeze. This is a fundamental principle of cometary physics, observed for centuries and considered entirely routine. Oumuamua, however, does not exhibit a conventional tail. It possesses something entirely different. On July 21, 2025, The Hubble Space Telescope captured an image of oumuamua. The image reveals a teardrop-shaped envelope of dust surrounding the nucleus. However, this envelope is not symmetrical. There is a greater concentration of material in front of the object, facing the sun, than behind it. The dust appears illuminated ahead of the nucleus, akin to headlights. This is contrary to expected behavior. Dust should trail behind. Radiation pressure should expel it away from the sun, creating a tail that streams backward along the orbital path. Instead, there is an illumination originating from the front, as if the object is internally illuminated or actively emitting material forward. Dr. Loeb proposes a potential explanation. If the nucleus does not rotate, consistently presenting the same face towards the sun, then the sun-facing side would remain perpetually heated, while the opposite side would remain perpetually cold. Ice on the sunlit side would sublimate, transitioning directly from solid to gas. This gaseous emission would carry dust particles with it. If the nucleus is not rotating, this outgassing would occur exclusively on the forward-facing side, the side exposed to the sun, thereby generating a forward illumination rather than a trailing tail. However, this explanation presupposes that the nucleus is tidally locked, similar to the Moon's synchronous rotation with Earth. Tidal locking occurs when an object orbits in close proximity to a significantly larger body for an extended period. The gravitational forces exerted by the larger body gradually slow the smaller object's rotation until its rotational period matches its orbital period. But oumuamua is not in orbit around any object. It is merely passing through. It has not had sufficient time to undergo tidal locking. Thus, why would its rotation cease unless it was intentionally designed to do so? Unless the object is deliberately maintaining a fixed orientation, consistently pointing one side towards the sun because that side is equipped with something, perhaps solar panels, sensors, or a transmitter. The illumination itself presents another puzzle. The Hubble image displays no prominent tail extending backward. For a comet that is already exhibiting activity at a distance of more than 4 astronomical units from the sun, a significant dust trail would be anticipated by this point. However, it is either absent or considerably less pronounced than expected. The illumination is concentrated around and in front of the nucleus, rather than streaming behind it. This observation is inconsistent with the established cometary model. It aligns with something else entirely. Anomaly number 5, the mass problem. On September 25, 2025, Dr. Avi Loeb published another paper, co-authored with Richard Cloutier and Peter T. Peter. This study meticulously analyzed the trajectory of oumuamua, utilizing data from 227 observatories worldwide. The research incorporated over 4,000 individual observations collected between May 15 and September 23. The objective was to detect non-gravitational acceleration. Non-gravitational acceleration occurs when a comet expels gas. The escaping gas acts like a miniature rocket, imparting a slight deviation to the comet's path, which would otherwise be dictated solely by gravitational forces. This is a common phenomenon observed in comets. By measuring the object's position over time and comparing it to its predicted gravitational orbit, the deviation reveals the thrust generated by the outgassing process. Oumuamua is losing mass. The James Webb Space Telescope measured the expulsion of approximately 150 kilograms of gas per second into space. This represents a substantial efflux of material from its surface. With such a significant rate of mass loss, one would expect to observe measurable non-gravitational acceleration. The outgassing jets should be exerting a force on the nucleus, causing minor deviations in its orbital path. However, Dr. Loeb and his colleagues detected no deviation whatsoever. 0. The path of the celestial body designated as 3I Atlas adheres strictly to the principles of Newtonian physics, within the limits of our observational precision. Despite a substantial loss of matter at a rate of 150 kilograms per second, the object is not exhibiting any acceleration. This singular observation points to a definitive conclusion. Its immense mass renders it impervious to the forces generated by its outgassing jets. The propulsion derived from the vaporization of its materials is utterly insignificant when contrasted with the sheer inertia of its core. When one performs the necessary calculations, factoring in the measured rate of mass depletion and the established upper boundary for acceleration, a minimum mass for 3I Atlas emerges, calculated to be no less than 33 billion tons. 33 billion tons. This figure is commensurate with the mass of a substantial mountain. Assuming a solid density composed of rock or ice, this implies a diameter of at least 5 kilometers or 5,000 meters. If 3I Atlas is indeed a solid entity spanning 5 kilometers, it represents a colossal structure, vastly exceeding the size of previous visitors from beyond our solar system. Oumuamua, the very first object of interstellar origin detected in 2017, was estimated to be a few hundred meters in length. 2I/Borisov, the interstellar comet identified in 2019, possessed a nucleus perhaps half a kilometer across. 3I Atlas dwarfs these predecessors, being an order of magnitude larger, 10 times the diameter, 1,000 times the volume, and 1,000 times the mass. However, this presents a significant statistical quandary. Smaller celestial bodies are demonstrably more prevalent than larger ones. Across the asteroid belt, the Kuiper belt, and interstellar space, the distribution of sizes follows a power law. For every sizable object, there exist thousands of smaller counterparts. We have, to date, identified 3 interstellar objects. 2 of these were diminutive. Now, suddenly, the third one is measured at 5 kilometers or more in diameter. This observation runs counter to our expectations. Logically, we should have encountered hundreds or thousands of smaller interstellar entities before encountering one of this magnitude. The statistical probability of detecting a 5-kilometer-sized object within a sample group of 3 is astronomically improbable. This leads to the unsettling possibility that 3I Atlas is not a random celestial occurrence. Its size may not be a mere coincidence. It might be of this scale because it was deliberately constructed to be this size, perhaps to accommodate a payload, or because it serves a purpose that necessitates substantial mass and structural integrity. When we collate all 5 observed anomalies, a compelling picture begins to emerge. The alignment with the ecliptic plane, an event with a probability of 1 in 500. The timing of its planetary encounter, occurring with a probability of 1 in 20,000. The specific timing of its perihelion passage, strategically obscuring it from observation during a critical juncture. The peculiar forward glow that defies conventional cometary physics. And finally, the anomalous mass that challenges statistical expectations. Each of these anomalies, when considered in isolation, is highly improbable. However, when viewed collectively, they begin to form a discernible pattern. And it is patterns that we actively seek when searching for evidence of intelligence. Consider the simple act of crossing a street. If there is a 40% chance that a vehicle will strike you, your attention is immediately drawn to that vehicle. You do not dismiss the risk and assume everything is safe. You remain vigilant. This is precisely the situation we find ourselves in with 3I Atlas. The anomalies are accumulating. The probabilities increasingly favor explanations beyond natural phenomena, and we are on the cusp of obtaining our closest ever examination. In mere days, cameras situated on Mars will capture images offering a resolution 100 times superior to anything we have previously achieved. We will finally be able to discern the nucleus separate from its surrounding dust cloud. We will ascertain whether its diameter is indeed 5 kilometers or something entirely different. And this newfound knowledge possesses the potential to fundamentally alter our understanding of what is theoretically possible. Chapter 3. The chemical fingerprint of technology. When analyzing a comet, its composition is determined by examining the light it emits and reflects through a process known as spectroscopy. This involves dispersing the light into a spectrum, akin to a rainbow, and searching for specific dark absorption lines or bright emission lines at particular wavelengths. Each chemical element and molecule possesses a unique spectral signature. For instance, sodium emits a yellow glow, hydrogen radiates red light, and water exhibits distinct absorption bands in the infrared spectrum. By identifying which wavelengths are present and which are absent, scientists can deduce the object's elemental and molecular makeup. Comets are predominantly composed of ice and rock, primarily water ice, interspersed with compounds like carbon dioxide, carbon monoxide, methane, ammonia, and dust particles comprising silicates and organic matter. As a comet draws nearer to the sun and its temperature rises, these ices undergo sublimation, transitioning directly from a solid to a gaseous state without melting. This liberated gas, carrying dust particles with it, forms the characteristic coma and tail. By scrutinizing the spectrum of this expelled gas and dust, we gain insight into the comet's composition. 3I Atlas has been observed by a multitude of telescopes since its initial detection. The Hubble Space Telescope imaged it in visible light. The James Webb Space Telescope provided observations in the infrared spectrum. The Very Large Telescope in Chile captured spectra revealing emission lines indicative of specific molecules. NASA's Sphere-X Space Telescope measured its brightness across multiple infrared wavelengths. Each subsequent observation has contributed another piece to the puzzle, and this puzzle is proving exceptionally difficult to assemble. Let us commence with its gaseous composition. On August 6, 2025, the James Webb Space Telescope utilized its near-infrared spectrograph to observe 3I Atlas. The Webb telescope boasts extraordinary sensitivity, capable of detecting faint molecular signatures that elude other instruments. The resulting spectrum revealed the presence of carbon dioxide, water, carbon monoxide, and carbonyl sulfide. While these substances are commonly found in comets, their relative proportions were highly irregular. The observed composition consisted of 95% carbon dioxide and 5% water, with only trace amounts of carbon monoxide and carbonyl sulfide. This composition is the inverse of what is typically observed in comets within our solar system, which are predominantly water-rich. Water is the most abundant volatile component in comets, a logical consequence of water ice being a common constituent in the frigid outer regions of planetary systems where comets originate. Carbon dioxide is present, but usually as a minor element. A typical comet might be comprised of 80% water, 10% carbon dioxide, and 10% other substances. 3I Atlas, conversely, is 95% carbon dioxide and a mere 5% water. This inversion is profoundly anomalous, akin to discovering a human being whose body is predominantly bone, comprising 95% with only 5% water. It is chemically perplexing. Stephanie Millam, an astrochemist at NASA's Goddard Space Flight Center who was involved in the Webb observations, proposed that the surface of 3I Atlas might have undergone alteration due to cosmic ray bombardment during its extensive journey through interstellar space. Cosmic rays are high-energy particles, predominantly protons, that traverse the galaxy at speeds approaching the speed of light. Upon impact with ice, they can fracture chemical bonds, leading to the formation of new molecules. Over millions or even billions of years, this radiation could effectively cook the surface, transforming some of the water ice into carbon dioxide and other compounds. Millam referred to this as a cooked shell. While this hypothesis is plausible, it encounters several significant challenges. Firstly, cosmic ray bombardment primarily affects the surface layer, not the interior of the object. As the comet begins to outgas, the superficial layer is expected to be rapidly ablated, exposing fresh, internal ice that has not been subjected to this radiative alteration. Consequently, the observed spectrum should evolve over time, initially showing a dominance of carbon dioxide and subsequently transitioning to a water-rich composition as the surface material dissipates. However, 3I Atlas has been actively outgassing for several months, and its spectrum continues to be overwhelmingly dominated by carbon dioxide. If anything, the production of carbon dioxide appears to be escalating as the object approaches the Sun. Secondly, other interstellar objects have not exhibited this phenomenon. 2I/Borisov, the preceding interstellar comet, displayed a composition remarkably similar to that of solar system comets, being water-rich with normal ratios of other volatiles. If cosmic ray-induced surface alteration is a universal process for interstellar objects, why does Borisov appear normal while 3I Atlas presents such a peculiar spectral signature? The magnitude of this effect, a 95% carbon dioxide concentration, is extreme. To convert such a substantial quantity of water ice into carbon dioxide would necessitate intense radiation exposure over an extended period. Furthermore, even under such conditions, one would anticipate a mixture of reaction products rather than a singular compound like carbon dioxide. The chemical explanation, therefore, does not entirely align. Consequently, one might consider that the surface was indeed altered by cosmic rays. Alternatively, it is conceivable that 3I Atlas originated within a planetary system where carbon dioxide ice was more abundant than water ice. Such conditions could arise in specific temperature zones of a protoplanetary disk. However, this scenario is unusual. Water is generally abundant due to the prevalence of oxygen, and hydrogen is the most abundant element. To produce a carbon dioxide-rich comet requires highly specific circumstances, which, while not impossible, are certainly not commonplace. Another possibility is that the carbon dioxide is not being released from ice, but is being generated through a different mechanism. This could involve chemical reactions, the decomposition of organic material, or even an artificial process, such as the venting of propellant. Carbon dioxide is indeed utilized as a propellant in spacecraft thrusters due to its stability, ease of storage, and capacity to provide a reasonable level of thrust. If 3I Atlas were a spacecraft, releasing carbon dioxide would represent a method of propulsion that avoids generating a conspicuously bright rocket exhaust. This is, of course, a speculative proposition. I am not asserting its veracity. Rather, I am highlighting the anomalous nature of the carbon dioxide dominance and the fact that our current explanations are not entirely satisfactory. Keep this possibility in mind as we examine further anomalies. Now, let us turn our attention to the nickel. On August 25, 2025, the Very Large Telescope in Chile, utilizing its UVS spectrograph, observed 3I Atlas. UVS, standing for Ultraviolet and Visual Echelle Spectrograph, is a high-resolution instrument capable of resolving minute details within a spectrum. The research team, led by Rohan Rahat Gammer and Thomas Puzier, detected emission lines originating from nickel atoms within the comet's coma. 22 distinct spectral lines were identified, all consistent with neutral nickel atoms fluorescing under solar ultraviolet radiation. The presence of nickel was unequivocally confirmed. Nickel in comets is not an inherently surprising discovery. Comets contain dust particles composed of rocky and metallic substances. When these particles are heated, either by solar radiation or through collisions within the coma, they can release atoms of various elements, including nickel. Nickel has been detected in other comets. Sodium, iron, magnesium, calcium, and nickel are all observable in cometary spectra when subjected to careful analysis. What is truly remarkable, however, is that the Very Large Telescope detected nickel but found no trace of iron. Iron is typically detected in conjunction with nickel, as they are chemically similar and are formed together during stellar nucleosynthesis. When a massive star undergoes a supernova, it produces both nickel and iron in roughly comparable quantities. Our solar system, and presumably other planetary systems, inherit this ratio. Rocky material, whether found in planets, asteroids, or comets, contains both nickel and iron. Every comet that has been studied in detail exhibits both iron and nickel. While the relative abundance may vary, the co-occurrence of both elements is a universal characteristic. The detection of nickel without any detectable iron is unprecedented in natural celestial objects, except in the case of 3I Atlas, where the VLT spectrum shows robust nickel emission and a complete absence of iron emission. The spectral lines that should be present for iron are conspicuously missing. The research team conducted a thorough examination, searching for iron lines across multiple wavelengths. No iron was detected. The established upper limits for iron abundance are sufficiently stringent that if iron were present at the same level as nickel, it would have been unequivocally detected. Its absence is therefore significant. Thomas Puzzia, one of the lead astronomers involved in the observation, remarked that this discovery opens a door to a whole new world of chemistry that we never had access to before. His assessment is accurate. However, the critical question remains whether this novel chemistry is a product of natural processes or artificial manipulation. On Earth, nickel is produced industrially without significant iron content. Nickel refining processes utilize chemical methods to separate nickel from iron ore. For example, the Mond process employs nickel carbonyl, a gaseous compound, to extract pure nickel. Nickel carbonyl is formed when carbon monoxide reacts with nickel at moderate temperatures. This gas is subsequently decomposed at higher temperatures, precipitating pure metallic nickel. This is a standard industrial technique. Nickel alloys used in aerospace and engineering applications often consist of high-purity nickel with minimal iron content. Components such as stainless steel jet engine parts and structural materials for spacecraft frequently incorporate refined nickel. The observation of nickel in the absence of iron strongly suggests industrial processing. Avi Loeb explicitly articulated this point, stating that nickel without iron is a signature of industrial production of nickel alloys. It is what you would expect from technology, not from a natural rock. Furthermore, 3I Atlas is expelling this substance at an escalating rate. When first detected in July, at an approximate distance of 3.9 astronomical units from the Sun, the nickel emission was faint. By late August, when it had approached to within approximately 2.8 astronomical units, the production rate had increased 25-fold. 25 times more nickel was detected in just 1 month. The closer it draws to the Sun, the greater the quantity of nickel it releases. This rate of increase is also anomalous. The VLT research team fitted the collected data to a power law function. The nickel production rate is observed to vary as the inverse of the heliocentric distance raised to the power of approximately 9. That is, distance to the power of -9. This represents an exceptionally steep dependence. For comparative purposes, typical cometary activity follows a scaling relationship of distance to the power of -2 or -3. An exponent of -9 signifies that the activity is escalating far more rapidly than expected as 3I Atlas approaches the Sun. What could account for such a dramatic surge in nickel production? One potential explanation is that the object's surface is stratified. It is conceivable that the outermost layer is rich in nickel and depleted in iron, and as this layer sublimates, it exposes underlying material with the same composition, thereby increasing the observed emission. However, this explanation necessitates accounting for why the surface is nickel-rich in the first place and does not address the fundamental absence of iron. Another possibility, proposed by the VLT research team, involves nickel carbonyl. If the surface harbors nickel carbonyl molecules, these compounds are exceptionally volatile. They sublimate at very low temperatures, significantly lower than that of water ice. Consequently, nickel carbonyl could be outgassing even when the comet is at a considerable distance from the Sun. As the ambient temperature rises, the production rate would increase exponentially. Upon decomposition, nickel carbonyl releases nickel atoms, which then fluoresce when exposed to sunlight, generating the observed emission lines. Nickel carbonyl is a legitimate molecular compound. It exists and is utilized in industrial nickel refining processes. The pertinent question is whether it occurs naturally within comets. We have never detected it previously, neither in comets within our solar system nor in interstellar space. While chemically plausible, its presence would be observationally unprecedented. And here lies a crucial point. If nickel carbonyl is indeed present in 3I Atlas, from what source did it originate? Carbonyl compounds are formed through the reaction of carbon monoxide with metals, a process that typically requires specific temperature and pressure conditions that may not be common in the frigid environments where planets form. Alternatively, these conditions might be more prevalent than we currently understand, and we simply have not conducted sufficiently detailed observations. Then there is the matter of its color transformation. In early September, astronomers Michael Jerger and Gerald Roman captured images revealing that 3I Atlas had shifted from a reddish hue to a vivid green luminescence. In comets, a green coloration is typically attributed to diatomic carbon molecules or cyanogen. The Very Large Telescope detected a sharp increase in cyanide production around the same period. The fluorescence of cyanide, specifically the carbon-nitrogen bonds, when exposed to sunlight, produces this characteristic green glow. The simultaneous escalation of cyanide production alongside nickel production, both exhibiting extreme rates of increase as the object nears the sun, and both displaying chemical signatures that are either unusual or entirely novel, reinforces a persistent pattern. Each new observation introduces an element that deviates from the conventional cometary model, or fits it so imperfectly that one must invoke extraordinary circumstances, exotic chemical processes, or exceedingly rare conditions, phenomena previously unobserved. At a certain juncture, one must question whether we are accumulating an excessive number of exceptional cases. Perhaps the most straightforward explanation is not that this is an extraordinarily peculiar comet with uniquely anomalous chemistry, formed under exceptionally rare conditions, but rather that it is something entirely different. Something that was never a comet to begin with. Chapter 4. The Loeb Scale. How perilous is it? When Avi Loeb began to consider 3I Atlas as potentially technological in origin, he recognized the necessity for a structured framework, a method to convey the level of concern without resorting to unfounded alarmism or neglecting a genuine potential threat. Consequently, he developed what is now known as the Loeb Scale, a classification system ranging from 0 to 10, designed to quantify the likelihood and potential danger of interstellar objects being artificial in nature. A rating of 0 on the scale signifies a definitively natural object, exhibiting properties consistent with recognized categories of comets or asteroids. 2I/Borisov, the prior interstellar comet, would be classified as a 0. It appeared as a comet, behaved like a comet, and possessed the chemical characteristics of a comet. There were no anomalies, no perplexing aspects, simply an icy body from another star system traversing our local space. A rating of 10 on the scale designates a confirmed artificial object on a direct collision course with Earth, possessing the potential for global catastrophic consequences, an existential threat. This scenario would necessitate an immediate and comprehensive response from humanity, deploying all available resources, though such a response might ultimately prove insufficient. Between 0 and 10, the scale progresses through escalating levels of anomaly and potential threat. Level 1 encompasses objects exhibiting minor deviations or yielding inconclusive data. Level 2 describes unusual properties that still fall within the established parameters of natural phenomena. Level 3 denotes persistent anomalies, features that challenge our current models but do not yet necessitate the postulation of a technological explanation. Level 4 is the current designation for 3I Atlas. According to Loeb's scale, Level 4 indicates the presence of multiple anomalies that are difficult to explain through natural processes. A pattern is emerging that suggests a potential artificial origin, though confirmation is still lacking. This corresponds to a 40% probability of technological origin and a 60% probability of it being a natural, albeit exceptionally unusual, celestial body. Reflect on this for a moment. 40%. If you were contemplating crossing a street and were informed of a 40% chance of being struck by a vehicle, you would undoubtedly refrain from crossing. You would pause, observe, and treat the potential danger with utmost seriousness, even though the likelihood of remaining unharmed is greater. Level 5 would be attained if additional evidence tips the balance beyond 50%, indicating further anomalies, stronger indicators, or behaviors that cannot be accounted for by any known natural process. Level 6 signifies that the object is very likely artificial, based on multiple independent lines of evidence, although not yet proven beyond any reasonable doubt. Level 7 represents the threshold of confirmed technology. At this level, the object would have demonstrably maneuvered in ways that require propulsion systems, transmitted signals, or display geometries or behaviors that are unequivocally artificial. At level 7, the scientific debate would cease. We would possess conclusive proof of its technological nature. The subsequent inquiry would then focus on its classification and its intended purpose. Level 8 designates a confirmed artificial object that poses no immediate danger to Earth. This could be a flyby mission, perhaps a probe observing us from a safe distance. While still representing a monumental discovery with profound implications for humanity, it would not constitute an immediate threat to our survival. Level 9 is assigned when a confirmed artificial object is on a trajectory that could inflict regional devastation, with an impact equivalent to a major nuclear detonation. Such an event could devastate a city or an entire country, but not bring about the end of civilization. Level 10, as previously stated, represents the highest possible designation. This signifies a confirmed artificial body on a direct collision course with Earth, with consequences of global magnitude. The asteroid responsible for the extinction of the dinosaurs was approximately 10 kilometers in diameter. 3I Atlas, with its potential size of 5 kilometers or more, if on a collision course at 60 kilometers per second, would unleash energy equivalent to millions of nuclear weapons. The subsequent dust cloud would obscure sunlight for years, leading to a drastic reduction in global temperatures, the collapse of agricultural systems, and ultimately, an extinction-level event. However, it is crucial to note that 3I Atlas is not currently on a trajectory that poses a direct threat of collision with Earth. Its current path will maintain a distance of at least 1.8 astronomical units from our planet, approximately 270 million kilometers. This distance exceeds the separation between the Earth and the Sun. Therefore, even if it were artificial and harbored hostile intentions, it is not presently aimed at us. Nevertheless, trajectories are not immutable. This is precisely why the perihelion maneuver is of such critical importance. If 3I Atlas were to execute a propulsion burn behind the Sun in late October, it could potentially alter its orbital path. Loeb and his colleagues have calculated the velocity change required to reach Earth. A delta V, or change in velocity, of 30 to 40 kilometers per second during October could direct the object, or components thereof, towards Earth between late December of 2025 and early January of 2026. A delta V of 30 to 40 kilometers per second is a substantial velocity change. This surpasses the capabilities of current human spacecraft utilizing chemical rockets, but it is not entirely unattainable. Advanced propulsion systems, such as ion drives, nuclear thermal propulsion, or more exotic technologies, could achieve such velocities. Moreover, given that 3I Atlas has been traversing interstellar distances for millions of years, it is reasonable to assume it possesses some form of propulsion system that enabled such long-duration travel. The timing of a potential arrival is also a critical factor. If an object were to arrive at Earth in late December or early January, our window for detection and response would be extremely limited. The window for observation is exceedingly brief, perhaps a mere few weeks at most. This duration is entirely contingent upon the reflectivity of the celestial body in question and the serendipity of our telescopes being precisely aimed in its direction. Such a fleeting time frame is utterly insufficient for the mobilization of any defensive measures. Our current infrastructure lacks the capacity to intercept an object spanning 5 kilometers and traversing interstellar distances at immense velocities. We possess only rudimentary capabilities to alter the course of much smaller asteroids moving at considerably slower speeds. Therefore, reaching level 4 on the Loeb scale, while not a cause for outright panic, signifies a yellow alert. It represents an acknowledgement of an anomaly, a deviation from the norm that warrants our immediate attention and diligent observation. This situation could very well escalate should such anomalies continue to manifest. Now, let us delve into the intriguing dark forest hypothesis, as it holds significant relevance to our considerations regarding potential threats posed by visitors from beyond our solar system. This hypothesis offers a proposed resolution to Fermi's paradox, that perplexing question of why, despite the sheer immensity of stars and planets within our galaxy, we have yet to encounter any definitive evidence of extraterrestrial civilizations. Popularized by the science fiction author Liu Cixin in his novel, The Dark Forest, the hypothesis posits the universe as a vast, dark forest. Each civilization within this cosmic expanse is akin to a hunter, stealthily navigating the trees, driven by the imperative of survival. The forest teems with other unseen hunters, their intentions shrouded in mystery. Any civilization that betrays its presence by making noise risks becoming a target for another hunter who perceives it as a potential threat. The underlying logic is starkly brutal, yet elegantly simple. Resources are inherently finite. Any civilization that expands its reach will inevitably enter into competition for these limited resources. Upon encountering another civilization, one faces a binary choice: cooperation or the elimination of a potential adversary. However, cooperation necessitates trust, which in turn requires communication. And communication, given the immutable constraints of the speed of light, is a protracted affair. Decades, or even centuries, might elapse between the transmission of a message and the reception of a reply. During this intervening period, the other civilization could be developing advanced weaponry or expanding its territory towards your own. Consequently, the most prudent strategy under these assumptions is to strike first. If a civilization detects another, it must neutralize it before it can evolve into a threat. This dynamic engenders a powerful selection effect. Civilizations that reveal themselves are annihilated. Those that maintain silence persist. Over eons, the galaxy becomes populated by silent, perpetually wary civilizations, each concealed within the dark forest, fearful of making the slightest sound. This paints a grim, unsettling picture. It suggests that our inaugural encounter with an alien civilization might not involve a benevolent exchange of knowledge and culture. Instead, it could manifest as a preemptive strike by a civilization that perceives us as a potential danger and opts to neutralize us before we pose a significant threat. Is the dark forest hypothesis an accurate reflection of reality? We cannot definitively say. It remains speculative, rooted in game theory and assumptions about the behavior of advanced civilizations. Nevertheless, it is not an entirely implausible scenario. Human history provides ample evidence that when technologically advanced civilizations encounter less advanced ones, the outcomes are frequently catastrophic for the latter. The patterns of colonialism, conquest, and exploitation are recurring themes. If 3I Atlas is indeed a probe from an advanced civilization, what are its ultimate intentions? Is its purpose to observe, to communicate, or to assess our potential as a threat? Or does it harbor more sinister objectives? Liu Cixin also introduced the concept of 3I Atlas potentially being a colossal mothership, a vast carrier capable of deploying smaller probes as it navigates the solar system. These smaller probes could be dispatched to investigate planets, moons, or other objects of interest. They might function as reconnaissance drones, or perhaps even as instruments of destruction. We would remain oblivious until their deployment. The calculated trajectory of 3I Atlas lends credence to this possibility. Its proximity to Mars, Venus, and Jupiter suggests that any smaller probes ejected from the main body could reach these planets with minimal supplementary thrust. A probe launched towards Mars when 3I Atlas is at its closest approach would require a delta V of merely a few kilometers per second to intercept. This is readily achievable with basic chemical propulsion systems. Earth presents a more complex scenario, as 3I Atlas never ventures particularly close to our planet. However, through orbital maneuvers during its perihelion passage, it could adjust its trajectory to release probes destined for Earth. Alternatively, it might have already released such probes months prior, remaining undetected due to our inability to detect objects smaller than approximately 100 meters. This underscores Liu Cixin's advocacy for enhanced surveillance. The Galileo project, which he spearheads, operates observatories dedicated to scanning the celestial sphere for unidentified anomalous phenomena. Should 3I Atlas deploy probes, and should these probes enter Earth's atmosphere or commence maneuvering in near-Earth space, the instruments employed by the Galileo project should be capable of detecting them. The project currently maintains 3 observatories, one situated in Massachusetts, another in Pennsylvania, and a third in Nevada. These facilities utilize a combination of optical and infrared cameras, alongside sophisticated algorithms, to identify and track objects exhibiting non-standard flight patterns. Conventional aircraft, satellites, and meteors all adhere to predictable trajectories and exhibit discernible characteristics. An extraterrestrial probe, conversely, would stand out distinctly. Its maneuvers would defy aerodynamic principles, and its emission or reflection of light would be anomalous. It would be detectable, provided we are actively observing. However, detection represents only the initial step. If alien probes are detected, what then? Do we attempt communication? Do we endeavor to capture one? Or do we perceive it as a threat and attempt to neutralize it? These are questions that demand consideration from governments and military strategists worldwide. Yet, as far as anyone can ascertain, no established protocols exist for managing alien technology within the vicinity of Earth's orbital space. The perihelion passage on October 29th is the pivotal moment. This is when 3I Atlas is anticipated to be most active, intensely heated by the sun and obscured from view behind the solar disk. If any significant actions are to be undertaken, this is the juncture at which they would occur. We will remain in ignorance until its reemergence in December. By that time, if probes have indeed been deployed, they could already be en route to Earth or other intended destinations. The imperative to prepare is now, not in the aftermath. Chapter 5. October 3rd, the Martian encounter. This very week, As you are listening, 3i Atlas is approaching Mars. Within days, possibly even hours, depending on the precise moment you are receiving this, the object will pass within 29 million kilometers of the red planet. While this may seem like a considerable distance, in astronomical terms, it constitutes an exceptionally close proximity. It is close enough for spacecraft currently orbiting Mars to capture images of unprecedented detail. The HiRISE camera aboard NASA's Mars Reconnaissance Orbiter serves as the crucial instrument. HiRISE, an acronym for High Resolution Imaging Science Experiment, represents one of the most formidable cameras ever dispatched to another planet. Engineered to survey potential landing sites for Mars rovers, it possesses the capability to discern features as small as 1 meter across on the Martian surface from orbit. However, on October 3rd, HiRISE will not be directed at Mars. Instead, it will be trained on 3i Atlas. From a distance of 29 million kilometers, it will achieve a pixel resolution of approximately 30 kilometers. This signifies that each pixel within the resulting image will represent roughly 30 kilometers of the object's surface. A resolution of 30 kilometers per pixel may not appear impressive when contrasted with the close-up imagery we receive of Mars, where individual boulders are clearly visible. Nevertheless, for an interstellar object traveling at 60 kilometers per second, this represents a groundbreaking advancement. No spacecraft has ever achieved such proximity to an interstellar visitor. During the passage of Oumuamua in 2017, we only detected it after it had already completed its closest approach to the Sun and was embarking on its outward journey. We obtained rudimentary images from ground-based telescopes, insufficient to resolve any surface features. 2i/Borisov was subjected to more detailed observation, but again, only from terrestrial telescopes, limiting its resolution. 3i Atlas presents a different scenario. We have spacecraft strategically positioned near Mars, and 3i Atlas is traversing directly past them. For the very first time, we will obtain a resolved image of an interstellar object. We will be capable of distinguishing the nucleus from the surrounding dust cloud. We will discern its shape, its surface topography, and the distribution of its brightness. If any substantial structures are present on its surface, if the object deviates from being a mere irregular agglomeration of rock and ice, HiRISE should be able to detect them. What precisely are we seeking? Several key elements. Firstly, its size. Current estimates for the nucleus of 3i Atlas range from approximately half a kilometer to 5.5 kilometers in diameter, a considerable degree of uncertainty. HiRISE will narrow this range by measuring the intensity of sunlight reflected by the brightest pixels and by assuming a plausible value for the surface reflectivity, known as albedo. Astronomers can then calculate the surface area of the nucleus. From this surface area and an assumed shape, they can estimate its diameter. If the nucleus proves to be at the larger end of the spectrum, 5 kilometers or more, the mass anomaly becomes particularly acute. As previously mentioned, discovering such a substantial interstellar object so early in our observational campaign is statistically improbable, thereby strengthening the argument that 3i Atlas is not a random celestial rock, but rather something intentionally constructed. Secondly, its shape. Natural comets and asteroids typically exhibit irregular, potato-like forms, characterized by cratered surfaces and rugged terrain. They are essentially rubble piles, collections of smaller fragments bound together by gravitational forces, or monolithic chunks of rock and ice that have been subjected to billions of years of impact events. If 3i Atlas possesses a highly regular geometric form, if it is spherical or cylindrical, or features flat surfaces and sharp edges, this would constitute a significant red flag. Artificial objects exhibit geometries that natural formations do not possess. Consider oumuamua. It was described as elongated, with a length-to-width ratio of approximately 10:1, resembling a cigar or a pancake, depending on the prevailing interpretation. Some researchers proposed it could be a fragment of a planet dislodged by tidal forces. Others suggested it might be a light sail, a thin, reflective sheet utilized for propulsion by reflecting solar radiation. The debate remained unresolved due to the inadequate resolution of the available images, which prevented us from discerning sufficient detail to differentiate between these possibilities. With 3i Atlas, we may finally acquire that crucial detail. If the HiRISE imagery reveals a regular geometry, if the object exhibits symmetries that natural processes cannot account for, it will become impossible to disregard. Thirdly, the dust cloud. HiRISE should be able to observe the distribution of dust surrounding the nucleus. Is it symmetrical? Is it concentrated in specific directions? Does it exhibit jets or plumes emanating from particular locations on the surface? Comets often display active regions, areas where subsurface ice is exposed, leading to outgassing. These jets can be highly directional, producing plumes that resemble geysers. If the dust cloud surrounding 3I Atlas displays an unusual structure, if there are jets pointing in directions that defy natural outgassing mechanisms, this would represent another anomaly to be added to the growing list. For instance, if jets are observed pointing sideways or backward relative to the sun, this would strongly suggest active maneuvering rather than passive sublimation. Fourthly, precursor objects. This is a speculative yet important consideration. If 3I Atlas has deployed smaller probes, and if these probes are positioned ahead of the main object on trajectories leading toward Mars, HiRISE might be able to detect them. Ground-based telescopes are incapable of resolving objects smaller than approximately 100 meters at the distance of Mars. However, HiRISE, from its vantage point in Martian orbit, can detect significantly smaller objects, provided they are sufficiently close and reflective. Avi Loeb has calculated that if 3I Atlas were to release a probe that traveled approximately 30 million kilometers ahead and laterally towards Mars, that probe could intercept Mars concurrently with the main object's closest approach. A probe moving at a mere few kilometers per second relative to 3I Atlas could cover that distance within the weeks or months since the object began exhibiting activity. Would HiRISE detect such a probe? Possibly. It depends on the probe's size and reflectivity, and whether it happens to fall within HiRISE field of view at the opportune moment. However, if a probe is present and we detect it, this would fundamentally alter our understanding. It would confirm the presence of technology, instantly elevating 3I Atlas to a considerably higher ranking on the Loeb scale. ESA's Mars Express and ExoMars Trace Gas Orbiter are also observing 3I Atlas during this encounter. Mars Express carries the high-resolution stereo camera and several spectrometers. ExoMars is equipped with the color and stereo surface imaging system and the Nomad spectrometer. These instruments will endeavor to measure the spectrum of light emanating from 3I Atlas, searching for specific molecular signatures within its coma. The spectrometers are capable of detecting molecules such as water, carbon dioxide, carbon monoxide, methane, ammonia, and various organic compounds. By comparing the spectrum observed from Mars orbit with spectra obtained from Earth-based telescopes and the James Webb Space Telescope, astronomers can construct a more comprehensive picture of its chemical composition. If molecules are present that were not previously detected, or if the ratios of molecules change as the object approaches the Sun, this information will be invaluable. It is cautioned that 3I Atlas will be relatively faint and distant. Thus, the imagery from Mars Express and ExoMars may not be particularly spectacular. The object will occupy less than a single pixel in their cameras, so we should not anticipate detailed surface imagery. However, the spectrometers may still yield valuable data, particularly if the coma is sufficiently bright. These observations are scheduled to occur from October 1st through October 7th, with the closest approach on October 3rd. By the time this broadcast reaches you, these observations may have already concluded. The acquired data will be downlinked from the spacecraft to Earth, subsequently processed and analyzed. The publication of the results is expected to take days or weeks. Nevertheless, upon their release, we will possess more information about 3I Atlas than we currently do. We will have empirical data to either corroborate or refute the observed anomalies. If the HiRISE imagery reveals a 5-kilometer nucleus with an irregular shape and a typical dust distribution, and if the spectral analysis indicates a standard cometary composition, then the technological hypothesis will be significantly weakened. It will not be entirely dismissed, as the trajectory and mass anomalies persist, but it will become considerably more challenging to argue for its artificial nature if it presents as an outwardly conventional comet. Conversely, if the HiRISE imagery discloses something unexpected, if the shape is too geometrically precise, if structures are present that should not exist, if the dust distribution is anomalous, or if there is any indication of precursor probes, then the technological hypothesis will gain considerable strength. We will ascend the Loeb scale, and the discourse will shift from mere speculation to a serious deliberation on the subsequent course of action. Furthermore, another spacecraft could potentially observe 3I Atlas, although it is situated further away, and a definitive decision has yet to be made. NASA's Juno spacecraft is presently in orbit around Jupiter. Juno's primary mission objective is to investigate Jupiter's atmosphere, magnetic field, and internal structure. However, its mission is drawing towards its planned conclusion. The spacecraft has significantly exceeded its original mission timeline and is experiencing a depletion of its fuel reserves. In March of 2026, 3I Atlas will pass in relatively close proximity to Jupiter, approximately 25 million kilometers away. While not as close as the encounter with Mars, it remains sufficiently near for Juno's instruments to observe the object. Juno is equipped with cameras, spectrometers, and a particle detector. It could conduct a more detailed analysis of the coma's composition, measuring isotopic ratios and trace elements that are difficult to detect from Earth. Avi Loeb and other researchers have advocated for redirecting Juno to intercept 3I Atlas. This would necessitate a trajectory alteration, involving a burn of Juno's engines to place it on a path that brings it into closer proximity with the object. Such a maneuver would need to be executed imminently, in mid-September or early October, to facilitate the March encounter. Following this encounter, Juno would lack sufficient fuel to return to its orbit around Jupiter. The spacecraft would effectively be sacrificed for this singular observation. NASA has not yet committed to this maneuver. The decision entails a careful balancing of trade-offs. Juno continues to gather valuable data pertaining to Jupiter. Terminating its mission prematurely to pursue an interstellar object represents a considerable gamble. Should 3I Atlas ultimately prove to be a mundane comet, the scientific community would likely question the wisdom of sacrificing Juno. However, if 3I Atlas turns out to be something extraordinary, the data acquired from a close encounter could prove to be immeasurably valuable. The observational data gathered from Mars, currently being acquired, will undoubtedly influence NASA's decision. If the data from October 3rd reveals significant anomalies, the argument for redirecting Juno will be substantially bolstered. Conversely, if the data indicates nothing out of the ordinary, NASA will likely maintain Juno's focus on Jupiter. Regardless of the outcome, we are on the precipice of acquiring a wealth of new knowledge concerning the nature of what we are confronting. Chapter 6. October 29th. The Solar Obscuration. Mark your calendars for October 29th, 2025. This is the date on which 3I Atlas will achieve perihelion, its closest approach to the Sun. For any comet, perihelion represents the most dramatic juncture of its celestial journey. The Sun's intense heat escalates, causing ice to sublimate at its maximum rate. The coma brightens considerably, and the tail extends further. This is the period when comets typically exhibit their most spectacular display, becoming most visible, most active, and most compelling to observe. However, in this instance, we will be deprived of this spectacle. On October 29th, 3I Atlas will be positioned on the opposite side of the Sun from Earth. The alignment of their respective orbits will place the Sun directly between our planet and the object. For several weeks both preceding and following its perihelion passage, 3I Atlas will be lost within the Sun's blinding glare, rendering it invisible to every telescope on Earth and every spacecraft operating within the inner solar system. This phenomenon is not entirely uncommon. Comets frequently traverse behind the Sun from our terrestrial vantage point. This presents a source of frustration for astronomers, as they miss the peak of cometary activity. However, it is a natural consequence of celestial mechanics. Orbits are dictated by gravitational forces, not by our observational convenience. Objects proceed according to the dictates of gravity. The peculiarity with 3I Atlas, however, lies in the timing of this obscuration. An object that has traversed vast interstellar distances over millions or even billions of years, an object whose trajectory aligns with the ecliptic plane to within a mere 5 degrees, an object that passes in close proximity to Mars, Venus, and Jupiter at precisely opportune moments, also happens to reach its closest approach to the Sun when it is entirely concealed from Earth's view. This represents yet another remarkable coincidence stacked upon a multitude of others. If one were tasked with designing a spacecraft with the objective of performing an action undetected, the period of perihelion behind the Sun would be the precisely chosen moment. Allow me to elucidate the rationale. A solar gravity assist maneuver is among the most efficient methods for altering velocity in space. The underlying principle is straightforward. When situated deep within a gravitational well and moving at high speed, a minor thrust from an engine produces a significantly greater change in the resultant velocity than the same thrust would achieve in the vacuum of deep space. It is analogous to pushing a swing at the lowest point of its arc versus pushing it at the apex. Timing is paramount. At perihelion, 3I Atlas will be approximately 1.4 astronomical units from the Sun, roughly 210 million kilometers. It will be traveling at its maximum relative speed to the Sun, approximating 90 kilometers per second at its closest approach. If its engines are fired at this precise moment, even a modest thrust, amplified by the principles of orbital mechanics, can affect a substantial change in its trajectory. How much thrust would be requisite to reach Earth? Avi Loeb has undertaken calculations to ascertain this. A velocity alteration of 30 to 40 kilometers per second, applied at perihelion, could place 3I Atlas, or any fragments ejected from it, onto a trajectory that intersects Earth's orbit. The anticipated arrival window would fall between late December of 2025 and early January of 2026. A delta V of 30 to 40 kilometers per second is substantial. Current human spacecraft, reliant on chemical rockets, are incapable of achieving such a velocity change. The fastest spacecraft ever constructed by humanity, the Parker Solar Probe, attain speeds of approximately 190 kilometers per second relative to the Sun. However, this speed is achieved after multiple gravitational assists from Venus and years of sustained acceleration. It does not possess an available 30 kilometers per second of delta V for maneuvering. But 3I Atlas is not a conventional human spacecraft. If it is artificial, it has been journeying through interstellar space for an extended duration. It presumably possesses propulsion systems that surpass our current technological capabilities, such as ion drives, nuclear engines, or antimatter propulsion. Some means capable of generating sustained thrust over prolonged periods or delivering high impulse burns when necessary. Would we be able to detect such a maneuver? It is a possibility, though not a certainty. Should propulsion be applied while the celestial body is obscured by the Sun, its expulsion trail would remain unseen. Consequently, any alteration in its path would not be observable in real time. Confirmation of a maneuver would only be possible upon its reappearance in December, after we reevaluate its orbital path. If the adjusted orbit deviates from the predicted one, indicating the object is not positioned as expected by purely gravitational forces, then a maneuver has indeed occurred. The fundamental issue is that by the time we detect such a maneuver, it will be too late to initiate a countermeasure. If 3 Atlas, or any debris it may release, were on a collision course with Earth, and our awareness only came in December, we would have a mere few weeks, at most, for preparation. No planetary defense system currently exists that is capable of intercepting an object 5 kilometers in diameter traveling at interstellar velocities with only a few weeks' warning. Even its initial detection would present a formidable challenge. 3 Atlas is an exceedingly faint entity, only becoming visible to our telescopes once it approached close enough and became active enough to reflect substantial amounts of sunlight. Should it release smaller probes, objects measuring tens or even hundreds of meters across, their detection would be significantly more difficult. We might not discern their presence until they are extremely close, potentially not until they have already entered the inner solar system or even breached Earth's atmosphere. This underscores why the LOE initiative strongly advocates for continuous celestial monitoring. The observatories associated with the Galileo project are expected to be actively scanning the heavens during the latter part of December and the beginning of January, specifically searching for anomalous objects. If any celestial body arrives, if probes or fragments are detected on an approach trajectory, their detection represents the crucial initial step towards any form of response. But what precisely would that response entail? This is the unsettling question that no one seems eager to address. There are no established protocols for confronting potentially hostile extraterrestrial technology on a trajectory towards Earth. We possess protocols for asteroid impacts, complete with early warning systems, models for predicting impacts, and theoretical strategies for deflection. However, these are designed for natural celestial bodies adhering to predictable orbital mechanics, objects we can track for years before they pose a threat. An alien spacecraft or its deployed probes would not adhere to these established principles. They possess the capability to maneuver unpredictably, to accelerate or decelerate at will, and to alter their course mid-flight. All our current asteroid deflection strategies are predicated on the assumption that the target is passive, that it will neither retaliate nor evade. The presence of an intelligent adversary fundamentally alters every equation. Furthermore, another scenario warrants consideration. What if 3I Atlas does not direct its trajectory towards Earth? What if it instead targets Jupiter? The path of 3I Atlas brings it relatively close to Jupiter following its perihelion passage. A modest alteration in velocity, perhaps 10 to 15 kilometers per second, could set it on a course that brings it considerably nearer to Jupiter than currently anticipated. This proximity would allow for detailed observation of the gas giant and its moons, and potentially facilitate the deployment of probes into Jupiter's atmosphere or onto the surfaces of Europa, Ganymede, or Callisto. Jupiter's moons are of immense interest to astrobiologists. Europa, in particular, with its hidden ocean beneath a thick ice shell, is regarded as one of the most promising locations within our solar system for the existence of life. If an extraterrestrial civilization were motivated to investigate the potential for life in our solar system, Europa would undoubtedly be a high-priority destination. A probe dispatched to Europa might be seeking precisely what we are: evidence of biological activity, microscopic organisms within its ocean, or chemical indicators of metabolic processes. If such life forms exist, and if 3I Atlas detects them, what would be the subsequent course of action? Would it transmit its findings back to its senders? Would it collect specimens? Could it inadvertently disrupt the existing ecosystem through contamination or environmental alteration? We are entirely unaware of their motivations, which constitutes the core problem. An advanced civilization capable of traversing interstellar distances possesses objectives that we can scarcely comprehend. They might be scientists, driven by an insatiable thirst for knowledge for its own sake. They could be resource acquisition agents, meticulously cataloging planets and moons for future exploitation. Alternatively, they might be exterminators, preemptively neutralizing potential competitors before they evolve into threats. The dark forest hypothesis posits this latter scenario. In a universe characterized by inter-civilizational competition for survival, broadcasting one's location or capabilities is inherently perilous. If 3I Atlas is an exploratory probe from such a civilization, its mission might well involve reconnaissance followed by neutralization, observe, assess, and if deemed necessary, eliminate. While this may sound like science fiction, and perhaps even paranoid conjecture, history demonstrates that when technologically superior civilizations encounter less advanced ones, the outcomes for the latter are frequently catastrophic. We have no grounds to assume that this historical pattern will not persist on an interstellar scale. Loeb does not assert definitive knowledge regarding the nature or purpose of 3I Atlas. Rather, he contends that we should refrain from dismissing the possibility of technological origin without thorough investigation. The perihelion passage on October 29 represents the pivotal moment. If the object is destined to reveal its true nature, if it is poised to perform an action inexplicable as natural cometary behavior, that is when it will occur. The significant challenge lies in our inability to witness this event unfold. We will be effectively blind during this critical period. Our only recourse is to await its reappearance in late November and early December, recompute its trajectory, and scrutinize for any deviations. If it adheres to its predicted path, exhibiting no indications of a maneuver, then perhaps the technological hypothesis loses some of its plausibility. However, if its position deviates from expectations, if its orbit has been altered in a manner necessitating the application of thrust, then we will have our answer. Subsequently, the more profound questions will emerge. Questions pertaining to our course of action, whether we attempt communication or prepare for defense, whether humanity can unite in the face of an external threat or fragment into competing factions debating response strategies. These are questions we have never been compelled to confront seriously, as the prospect of alien visitation was, until now, purely theoretical. 3I Atlas transforms it into a tangible reality. In less than a month, we will possess more information. We will have data from its Mars flyby. We will observe its behavior as it approaches the sun. And then, after it vanishes behind the solar disk, we will wait. We will watch, hoping that upon its reappearance, it will still be nothing more than a comet. Yet, we must also prepare for the possibility that it is not. Chapter 7. The Exploding Conspiracy Theories. When enigmatic events occur and official explanations fall short, the internet rapidly fills the void with speculation. 3I Atlas has become a focal point for conspiracy theories, with online chatter intensifying significantly in the past 48 hours. Across forums, social media platforms, and YouTube channels, countless theories are circulating about the true nature of the situation. Some of these theories are harmless musings, with individuals posing questions and drawing connections that may not be genuinely substantive. However, certain theories have gained considerable traction, spreading through communities already harboring skepticism towards official narratives. A subset of these theories touches upon a disquieting notion that information is being deliberately withheld, that the public is not being privy to the complete truth, and that clandestine activities are underway beyond public knowledge. I will outline these prevailing theories not as an endorsement, but to illustrate how we process uncertainty and perceive threats. The theory of deceleration posits that over the last 72 hours, claims have surfaced on platforms like Reddit suggesting that 3I Atlas is slowing down, its velocity relative to the sun diminishing in ways that cannot be attributed to gravity alone. If accurate, this would be a monumental revelation. Natural celestial bodies do not decelerate unless actively applying thrust in opposition to their direction of travel. While a comet might experience a slight acceleration due to outgassing jets, a reduction in speed necessitates backward engine firing, a capability comets do not possess. The primary challenge with these claims is their lack of credible sourcing. Individuals cite vague references to observations or purportedly leaked data without providing specific details. Attempts to trace the origin of these claims invariably lead to their dissipation. This does not inherently invalidate the claims, but it signifies their unverified status. In situations carrying high stakes, unverified assertions can be detrimental, potentially inciting panic or misdirecting critical attention. What is definitively known is that Loeb's research analyzed the object's trajectory up to September 23 and detected no measurable non-gravitational acceleration. Were 3I Atlas indeed decelerating, this would manifest as a deviation from its predicted orbital path within the available data. As of late September, no such anomaly was detected. This does not preclude a more recent maneuver, but it suggests that any observed deceleration would have commenced after the data collection cutoff. Then there is the pulse theory. Some individuals assert that 3I Atlas is emitting energy pulses at regular 17-minute intervals. These alleged 17-minute intervals are purportedly detected by radio telescopes or other instruments, though again, no official confirmation has been published. The 17-minute interval is notably specific, not a round number, and does not correspond to any easily identifiable natural period, such as a rotation rate or orbital resonance. If these pulses are indeed real, their natural explanation would be challenging. Pulsars emit regular pulses, but they are neutron stars with periods measured in milliseconds to seconds, not minutes. 17-minute pulses emanating from a small object would imply an active, artificial process, a mechanism that cycles on and off with precise regularity. This could be artificial, perhaps a beacon signaling the object's positional status, or a form of data transmission, sending information packets at set intervals. However, caution is paramount. Radio astronomy is inherently complex, and interference from terrestrial sources, such as satellites and ground-based transmitters, can generate false signals that appear to originate from space. Differentiating genuine extraterrestrial signals from terrestrial noise requires rigorous analytical processes. The WOW signal, for instance, was remarkable because it successfully passed all diagnostic tests, exhibiting appropriate characteristics, duration, and frequency. The 17-minute pulses, if they exist, would need independent verification from multiple observatories before being taken seriously. Another circulating theory pertains to transparency. Why is so little information being disseminated about 3I Atlas? NASA and other space agencies have maintained a relatively low profile. While official statements provide basic facts regarding its orbit and composition, detailed information is scarce. Some interpret this reticence as suspicious, suggesting that information is being deliberately concealed to avert public alarm. The counterargument is straightforward. Scientists operate with caution, refraining from premature publication before exhaustive data analysis. The peer review process is time-consuming. Telescopes and spacecraft collect data, which is then downloaded, processed, vetted for errors, analyzed, compiled into research papers, submitted to journals, reviewed by fellow scientists, and finally published. This entire procedure can span weeks or months. The Mars observations on October 3rd have only recently concluded, and the data is likely still undergoing processing. Instantaneous results should not be anticipated. Nevertheless, the perception of secrecy inevitably fuels speculation. In an era where information propagates instantaneously across social media and where individuals expect real-time updates, the conventional pace of scientific publication can appear slow, even evasive. Furthermore, there is the question concerning NASA's Juno spacecraft. Why is NASA not committed to redirecting Juno to intercept 3I Atlas in March? Such a maneuver is technically feasible, especially given that Juno is nearing the conclusion of its mission. The potential scientific yield from a close encounter with an interstellar object could be immense. So what accounts for the hesitation? Some attribute it to bureaucratic inertia. NASA, being a large organization, operates with committees and approval processes. Modifying a mission plan, even for a spacecraft nearing its operational end, necessitates endorsements from multiple hierarchical levels, a process that consumes time. Others point to budgetary concerns. Redirecting Juno would incur costs, and if the encounter yielded no significant findings, justification for the expenditure would be required. However, a more sinister interpretation, popular within conspiracy circles, suggests that NASA actively wishes to avoid a close approach. This viewpoint posits that they possess knowledge about 3I Atlas that renders a close encounter perilous or undesirable. Perhaps they harbor concerns about contamination, exposing the probe to unknown biological or chemical hazards. Alternatively, they might fear damage or destruction of the probe by the object itself, should it prove hostile. Or, perhaps the most unsettling possibility, they fear what Juno might discover, information that would be exceedingly difficult to suppress. It is crucial to state unequivocally that there is no evidence whatsoever to suggest NASA is withholding information. The more plausible explanation, that they are exercising caution and adhering to standard operational procedures, is far more likely. Nevertheless, perception holds sway. When individuals feel they are not being apprised of the truth, they tend to fill the informational void with their own narratives, some of which are profoundly unnerving. Additionally, there is discussion surrounding the Epstein files distraction theory. Certain individuals believe that the announcement concerning 3I Atlas and the associated media attention were deliberately orchestrated to divert focus from other news events, political scandals, or economic anxieties. They suspect that a conveniently timed alien scare is being employed to manipulate public attention. Loeb directly addressed this assertion in one of his blog posts, emphasizing that 3I Atlas is a tangible object observable by anyone possessing a reasonably capable telescope. It is not a fabrication, It exists in space, moves at a measurable velocity, and is subject to independent verification. It is not something that he or anyone else could fabricate through means such as a Jewish space laser or any other baseless fabrication. The object is real, its trajectory is accurate, and its anomalies are genuine. Whether these anomalies signify alien technology is a scientific inquiry, not a political one. However, conspiracy theories flourish in an environment of distrust, and distrust is unfortunately abundant. Individuals who lack faith in governmental institutions, who distrust scientists, and who have experienced deception in the past are unlikely to suddenly embrace official pronouncements regarding an interstellar object. They will inevitably assume deceit, hidden agendas, and the worst possible outcomes. The government hoax theory takes this skepticism a step further. A small but vocal contingent claims that 3I Atlas is entirely fictitious, a fabricated narrative, or a ruse designed to prepare the public for a staged alien invasion or to legitimize increased government surveillance and control. The Project Blue Beam theory, an older conspiracy narrative involving holographic alien invasions, has been resurrected and applied to 3I Atlas. This theory is easily debunked. Multiple independent observatories worldwide have detected and tracked 3I Atlas. Amateur astronomers have captured images of it. Were it a fabrication, it would necessitate a global conspiracy involving thousands of scientists and institutions across numerous countries, a level of coordination that is demonstrably implausible. Occam's razor dictates that the simpler explanation, that the object is real, is the correct one. However, for individuals already predisposed to distrust, no amount of evidence will suffice. They will assert that the images have been doctored, the data fabricated, and the scientists complicit. Once one embarks on such a downward spiral of suspicion, logical reasoning becomes ineffective. Another recurring theme is psychological acclimatization. The idea is that 3I Atlas, regardless of its actual origin, is being utilized to gradually acclimate the public to the possibility of extraterrestrial existence. This is seen as a form of staged disclosure, proceeding in increments. Initially, we discover exoplanets. Subsequently, we detect biosignatures in their atmospheres. Then, an interstellar object appears with unusual characteristics. Each step primes us for the next, progressively building towards the eventual revelation that humanity is not alone. Some individuals welcome this development, viewing it as a positive advancement, an expansion of human understanding, and a step towards integration into a galactic community. Others express apprehension, concerned about the profound implications for religious and philosophical frameworks, and the potential threats posed by advanced extraterrestrial civilizations. Hovering over all of this is a simple question. If 95% of the global population is unaware of 3I Atlas's existence, is this due to a lack of information dissemination or because the majority of people simply do not pay attention to astronomy news? The latter is the more probable reason. Unless space news involves dramatic imagery or immediate threats, it rarely captures mainstream attention. An interstellar object exhibiting anomalies is of great interest to those who closely follow space science, but to the general public, it remains an abstract concept. This situation could change rapidly if something dramatic were to transpire. Should 3I Atlas execute a maneuver, should probes be detected, or should any confirmed evidence of technology emerge, it would instantly become front-page news globally. At that juncture, conspiracy theories would proliferate exponentially, as the stakes would become undeniably real, and everyone would demand answers. Chapter 8. Scientists at War, the Academic Bloodbath. Science is ideally characterized by objectivity and dispassion, by rigorously following data wherever it may lead, and by testing hypotheses with utmost scrutiny, accepting results irrespective of whether they confirm or contradict pre-existing expectations. This represents the aspirational ideal. However, science is ultimately a human endeavor, and humans possess egos, reputations, and careers. When an individual challenges established consensus or proposes ideas that threaten prevailing thought, the repercussions can be severe. Avi has personally experienced this phenomenon. He is not the first scientist to face ostracism for holding unconventional views, nor will he be the last. However, the intensity of the backlash he has encountered, particularly concerning oumuamua and now 3I Atlas, exposes a disquieting aspect of how the scientific community confronts anomalies that resist categorization within existing frameworks. Let us begin with NASA's official response. Tom Statler, NASA's lead scientist for solar system small bodies, was questioned regarding the assertions that 3I Atlas might be of alien origin. His reply was dismissive. He informed reporters that 3I Atlas exhibits characteristics consistent with a comet, behaving as comets typically do, and bears a strong resemblance to known comets. While he acknowledged its possession of certain intriguing properties that differentiate it from solar system comets, He concluded that the overwhelming evidence points to its natural origin. On the surface, this response appears reasonable. Most anomalous celestial objects, upon detailed examination, are eventually identified as natural phenomena. Extraordinary claims necessitate extraordinary proof. To date, the evidence supporting the artificial nature of 3I Atlas remains circumstantial. However, note what Statler conspicuously omitted from his statement. He failed to address the discrepancy of the nickel without iron composition. He did not explain the synchronized trajectory alignment and coincidental timing. He offered no explanation for the mass anomaly or the observed antitail. He simply asserted its cometary appearance and concluded his assessment. This represents a recurring pattern. When scientists aim to discredit an idea without engaging with its specific details, they resort to broad generalizations. It appears normal, its behavior is as expected, and the alternative explanation is simply too far-fetched. However, a thorough examination of the data reveals that the specifics do not align with a straightforward cometary narrative. The details are indeed peculiar, and peculiarity warrants explanation, not mere dismissal. Jason Wright, an astronomer at Penn State University, has been more direct in his critique of Loeb. Wright maintains a blog named Astroblogger, where he discusses astronomical topics and occasionally reviews papers he deems problematic. He has authored multiple posts dissecting Loeb's arguments concerning 3I Atlas, employing a decidedly critical tone. In one particular post, Wright accused Loeb of disregarding evidence that contradicts his hypothesis. Specifically, Wright highlighted that Hubble telescope imagery clearly displays a coma surrounding 3I Atlas, the characteristic fuzzy envelope of gas and dust associated with comets. Loeb acknowledged the presence of the coma but contended that its distribution was unusual, exhibiting greater brightness in the forward direction than in the rear. Wright characterized this dismissal of the coma as mere smearing, as a far greater contrivance than simply ignoring the images altogether. Wright also took issue with Loeb's continued advocacy for the alien hypothesis. Even after spectroscopic data obtained from the James Webb Space Telescope and the Very Large Telescope indicated that 3I Atlas is emitting molecules such as carbon dioxide, water, and cyanide. The presence of these molecules, he argues, confirms its cometary nature. He questioned why an alien spacecraft would vent water and carbon dioxide, suggesting that the simplest explanation is sublimation, not propulsion. Loeb's counterargument posits that the observed chemical makeup is irregular. A composition of 95% carbon dioxide is not typical, nor is nickel found in isolation from iron. The mere act of the celestial body expelling volatile substances does not inherently prove its natural origin as a comet. It could conceivably be a constructed vessel, its exterior bearing a veneer of ice and cosmic detritus accumulated during its passage through interstellar space. As this outer layer warms, it releases gases, thereby simulating cometary behavior while concealing the artificial core beneath. Wright finds this proposition unconvincing. In his judgment, Loeb is constructing a series of unsubstantiated assumptions to uphold a hypothesis that ought to be discarded. Wright's correspondence indicates that Loeb's approach resembles that of individuals subscribing to conspiracy theories, who expect others to disprove their assertions rather than offering concrete evidence for their own. Wright contends that the onus rests upon Loeb to demonstrate that the object designated oumuamua is artificial, not upon the global scientific community to prove its natural classification. Steve Desch, a scientist specializing in planetary studies, took an even more critical stance. Upon reviewing one of Loeb's academic papers, he characterized it as substandard work, below the expected caliber of an undergraduate student. Desch, in a manner akin to grading a student's assignment, awarded the paper a failing mark. His critique encompassed the research methodology, the underlying assumptions, and the conclusions drawn. He furthermore accused Loeb of selectively presenting data that supported his claims while disregarding alternative interpretations. Such discourse diverges significantly from standard academic exchange. While peer review can be rigorous, publicly disparaging a colleague's research and likening it to elementary academic errors crosses a professional boundary. This suggests not merely a difference of opinion, but a profound disdain, prompting inquiry into the intensity of this reaction. If Loeb's theories are demonstrably flawed, why expend energy in public humiliation rather than simply ignoring them? One potential explanation is that Loeb's propositions are attracting considerable attention. Media outlets are reporting on his statements, and the public finds the notion of extraterrestrial origins captivating. When public enthusiasm is ignited by ideas considered marginal by the scientific mainstream, those scientists often feel a duty to counter, to rectify inaccuracies, and to prevent the proliferation of misinformation. However, another factor is also at play. Loeb is a recognized figure with a distinguished academic record that cannot be easily dismissed. He holds the position of a Harvard professor, formerly chaired the astronomy department, possesses a substantial publication history, and is highly cited. He is not an outlier operating on the fringes. He is part of the established academic order, or at least was. When an individual of such considerable credibility begins to advance claims that challenge established scientific consensus, it can undermine the gatekeeping role upon which academia relies. Scientific progress is fueled by the rigorous examination of novel concepts, leading to their validation or refutation. Nevertheless, science also possesses a conservative element, a resistance to ideas that deviate too far from prevailing thought. This conservatism serves a purpose by filtering out extraneous information and preventing every speculative notion from consuming valuable resources and attention. Conversely, it can also impede innovation, delay paradigm shifts, and penalize scientists who venture into uncharted territory. Loeb's scholarly contributions concerning oumuamua have encountered atypical impediments. One paper he co-authored with Eric Keto, which offered a physical explanation for the unusual antitail observed in Hubble telescope imagery, was rejected by a journal editor who stated that the findings would be of rather limited interest to the broader research community. This editorial statement serves as a veiled rejection, indicating an unwillingness to publish the work. Another paper, addressing the absence of non-gravitational acceleration and implying the presence of an anomalously massive object, was temporarily withheld by AR-14 moderators for several days without any stated reason. AR-14 is a platform for preprint scientific papers submitted before undergoing formal peer review. It is not intended to function as a barrier to publication. Submissions are typically processed quickly with minimal editorial scrutiny. In this particular instance, however, the paper's release was delayed, and upon its eventual publication, no explanation was provided for the holdup. These occurrences could be mere coincidences, or they might signify a concerted effort to impede the dissemination of Loeb's ideas, thereby granting mainstream scientists time to formulate counterarguments and control the narrative before it escalates. Loeb himself has directly addressed the criticisms leveled against him. He maintains that scientific inquiry should be driven by curiosity and intellectual openness, rather than by the enforcement of rigid doctrines. He emphasizes that anomalies are crucial catalysts for learning. By dismissing every anomaly as mere background noise or an error, we risk overlooking opportunities for groundbreaking discoveries. The history of scientific exploration is replete with examples of concepts initially met with ridicule that were subsequently proven correct, including continental drift, the Big Bang theory, and the existence of black holes, all of which faced significant skepticism before incontrovertible evidence emerged. Loeb also observes that his critics frequently fail to engage with the specific details of his arguments. They assert it is a comet without addressing the presence of nickel. They claim its trajectory is random without analyzing the probability calculations. They accuse him of speculation without acknowledging that his conjectures are grounded in empirical data and physical principles. Furthermore, there is a personal dimension to these criticisms. Some of Loeb's detractors have made disparaging remarks about him as an individual, not solely about his theories. They have questioned his motivations, suggested he is seeking personal notoriety, and accused him of detrimental to the scientific enterprise by lending credence to fringe concepts. An editor who handled one of his submissions publicly shared negative personal commentary. When Loeb lodged a complaint, the editor's superior defended the behavior as not falling outside ethical boundaries. This scenario exemplifies internal conflicts within academia. When a field feels threatened by unconventional ideas, the response can become intensely adversarial. Professional reputations are built upon sustained credibility, and these reputations are inherently fragile. Association with a controversial or erroneous theory can leave a lasting stigma. Consequently, scientists often protect themselves by distancing themselves from anything perceived as risky and by actively challenging those who do not adhere to cautious practices. However, what if Loeb's perspective is accurate? What if oumuamua is indeed artificial? And the scientific community has dismissed the evidence because it is too unsettling, too disruptive, or too far outside the established boundaries of acceptable discourse. The repercussions of such a misjudgment would be profound. We would forego the opportunity to prepare, to study, and to comprehend the nature of this encounter. Future historians would undoubtedly question how such a significant oversight could have occurred. Chapter 9. What if we are mistaken? An examination of natural explanations. To ensure fairness to the skeptics, I will present the most compelling arguments for classifying oumuamua as a natural celestial body, as this remains the most probable explanation. Extraordinary claims necessitate extraordinary evidence, and while the anomalies observed are intriguing, they have not yet reached the threshold of definitive proof. Scientific inquiry mandates the consideration of all plausible hypotheses, and the natural explanation merits a comprehensive evaluation. Let us begin with the chemical composition. A substance comprising 95% carbon dioxide and 5% water is indeed atypical for a comet. However, unusual does not equate to impossible. Comets originate in diverse regions of protoplanetary disks under varying temperature and pressure conditions. The proportion of volatiles is contingent upon the location and temporal circumstances of the comet's formation. A comet formed in a colder, more distant region of its parent star's system, where carbon dioxide ice is more stable than water ice, could exhibit a composition rich in carbon dioxide. The hypothesis of cosmic ray alteration also holds merit. Oumuamua has traversed interstellar space for potentially billions of years. Cosmic rays are an incessant force, bombarding any surface exposed to the vacuum of space, thereby breaking chemical bonds, synthesizing new molecules, and modifying elemental composition. Water ice subjected to cosmic rays can undergo radiolysis, transforming into carbon dioxide and other compounds. Over millions of years, the surface layer could become significantly altered. The dominance of carbon dioxide could arise while the interior retains its water-rich composition. The observed increase in carbon dioxide expulsion as the object approaches the sun might simply indicate that deeper strata are being exposed due to surface ablation. Alternatively, it could signify that subsurface reservoirs of carbon dioxide ice are being heated and venting through fissures in the crust. Comets are not monolithic entities. They possess layers, internal pockets, and compositional variations. The process of outgassing can be intricate and influenced by temporal factors. The detection of nickel without accompanying iron presents a greater challenge to natural explanations, yet it is not insurmountable. The team operating the Very Large Telescope has proposed nickel carbonyl as a potential source. Nickel carbonyl is a molecule that forms when nickel reacts with carbon monoxide. It is highly volatile, sublimating at exceptionally low temperatures. If oumuamua contains nickel carbonyl, perhaps formed through unusual chemical processes within its parent system or during its interstellar journey, this would account for the detection of nickel without iron. Iron might be present but bound within more stable compounds such as iron oxides, iron sulfides, or iron-containing silicates. These materials require higher temperatures to decompose and release iron atoms. If the current temperature of oumuamua is sufficient to vaporize nickel carbonyl but not high enough to liberate iron from its host minerals, then nickel emission would be observed without corresponding iron emission. As the object draws nearer to the sun and its temperature escalates, iron may subsequently become detectable in the spectral analysis. The alignment of its trajectory with the ecliptic plane, a statistical improbability of 1 in 500, sounds unlikely. However, with a sufficiently large sample size, improbable events do occur. If we observe hundreds or thousands of interstellar objects in the coming decades, it is reasonable to expect that a few will exhibit an alignment with the ecliptic purely by chance. Oumuamua might represent such a 1 in 500 instance. The temporal coincidence that brings it into proximity with Mars, Venus, and Jupiter, a rarity estimated at 1 in 20,000, presents a more significant challenge to dismiss. Nevertheless, again, with an ample number of objects, rare configurations are bound to manifest, and there may be selection biases at play that we are not currently accounting for. It is possible that interstellar objects that happen to align with the ecliptic and pass near planetary bodies are more readily detected because they approach Earth more closely and reflect a greater amount of sunlight. If our detection methodologies exhibit a bias favoring certain orbital configurations, these statistical assessments could be misleading. The issue of mass, wherein oumuamua is substantially larger than the two previously identified interstellar objects, could reflect the diversity inherent in interstellar populations. It is conceivable that smaller objects, such as oumuamua, and Borisov, are prevalent, while larger entities like oumuamua are infrequent. We have, to date, identified only 3 interstellar objects, a sample size far too limited to draw definitive conclusions regarding their size distribution. Perhaps we have been fortunate or unfortunate, depending on one's perspective, to encounter a large specimen early in our observations. The antitail, or forward glow, can be explained by asymmetrical gas expulsion from a non-rotating nucleus. If the nucleus is tidally locked or rotates slowly, and if the majority of gas expulsion occurs on the side facing the sun, a plume expanding forward will result. This plume scatters sunlight, generating the observed pattern of brightness. The absence of a pronounced tail might indicate a lower dust production rate than anticipated, or that the dust particles are larger and less susceptible to radiation pressure, thereby failing to form an extended trailing tail. Each anomaly presents a potential natural explanation. These explanations may necessitate the invocation of rare conditions, exotic chemical processes, or statistical anomalies, but they are not inherently impossible. When confronted with two hypotheses, one that relies on established physics and chemistry under unusual circumstances, and another that posits alien technology. Occam's razor advises us to favor the more straightforward explanation. The simpler explanation is that oumuamua is a comet. It is an anomalous comet, certainly, an ancient object from a different galactic sector with a composition and behavior previously unobserved, but a comet nonetheless. It is a natural entity shaped by billions of years of cosmic evolution, not an artificial construct. This is the prevailing stance adopted by most astronomers, and it is a reasonable position. It acknowledges the anomalies while maintaining that extraordinary claims demand extraordinary proof, and the evidence thus far falls short of that standard. We possess circumstantial evidence, suggestive patterns, and intriguing coincidences, but no irrefutable proof. There are no definitive indications of artificial structure, propulsion, or communication. The observations scheduled for late October and November are expected to yield additional data. The imagery from Mars, spectral analyses from ESA's orbiters, and continuous monitoring as the object passes perihelion and subsequently recedes will all contribute. Each new dataset will either bolster or weaken the natural hypothesis. If the data continues to align with the cometary model, if the object exhibits predictable behavior, and if no further anomalies arise, then the technological hypothesis will likely recede in prominence. However, if the data reveals something unforeseen, if new anomalies emerge, or if the object displays behavior inconsistent with comets, then we will be compelled to reassess. And this is precisely what Avi Loeb is advocating for. Not that his hypothesis be accepted as proven, but that we maintain an open mind and follow the evidence. There exists a middle ground between assuming every anomaly signifies alien activity and definitively ruling out the possibility of alien involvement in any anomaly. This middle ground comprises careful, unbiased investigation. It means acknowledging our present lack of knowledge and committing to finding answers. It entails recognizing that the universe is replete with surprises, and occasionally, these surprises profoundly challenge our existing understanding. One argument that I find particularly persuasive concerns the age of oumuamua. If it originated from the thick disk of the Milky Way galaxy, as its velocity and trajectory suggest, it could be between 7 and 11 billion years old. This would make it older than the Sun, older than Earth, and older than any object within our solar system, with the possible exception of certain extremely ancient asteroids that formed during the solar system's nascent stages. Such an aged object has been a witness to the galaxy's evolution. It has observed stars ignite and expire. It has traversed regions subjected to intense radiation, dense molecular clouds, and potentially even close encounters with other stars. Over such an immense temporal span, it has been shaped by processes that are difficult for us to fully comprehend. Its surface has undergone bombardment, erosion, and alteration. Its interior may have experienced phase transitions, chemical reactions, and structural reorganization. When dealing with an object of such antiquity, one cannot assume it will behave like the comets within our solar system, which are comparably infants at approximately 4.5 billion years old. The chemistry could be fundamentally different. The structure could be distinct. Every aspect could differ in ways we have not anticipated, simply because we have never studied an object of such advanced age from outside our solar system. Therefore, it is plausible that the observed anomalies are not indicative of technology, but rather of extreme age and extraordinary origins. It is conceivable that oumuamua serves as a testament to the universe's greater diversity than our current models encompass, demonstrating that natural processes can yield outcomes we have not predicted. Perhaps the lesson here is one of humility, an acknowledgement that our understanding of comets and interstellar objects remains in its infancy. Such a realization would be profoundly valuable, expanding our collective knowledge and refining our scientific approach. Moreover, it would avoid the necessity of fundamentally altering our worldview or confronting the disquieting possibility of being observed by intelligences far older and more advanced than our own. Chapter 10. Humanity at a Crossroads. What lies ahead? We are approaching a juncture of significant clarification. In the ensuing weeks, numerous spacecraft will conduct observations of oumuamua with unprecedented detail. The flyby of Mars on October 3rd will provide our initial resolved images. The perihelion passage on October 29th will ascertain whether the object behaves as a natural comet or exhibits unexpected characteristics. Its reappearance in late November and December will reveal whether its trajectory has undergone alteration. Each observation serves as a critical test, and each outcome will either validate or challenge our current understanding. Between November 2nd and November 25th, the European Space Agency's Jupiter Icy Moons Explorer spacecraft, designated JUICE, will observe oumuamua utilizing a suite of instruments. JUICE is presently en route to Jupiter, having completed flybys of Earth and Venus for gravitational trajectory adjustments. It is optimally positioned to view Oumuamua during one of its most active phases, shortly after perihelion, when the comet is expected to be at its peak brightness and outgassing rate. JUICE is equipped with cameras, spectrometers, and a particle detector. The cameras will capture images of the coma and any developing tail. The spectrometers will perform compositional analysis of the gas and dust, searching for molecules that may have been overlooked in earlier observations. The particle detector is capable of measuring ions and charged particles in the comet's vicinity, providing insights into the interaction between the solar wind and the expelled material. ESA asserts that JUICE will likely provide the most comprehensive view of Oumuamua in a highly active state, as it will be observing the comet post-perihelion, when it has experienced maximum solar heating. The activity is anticipated to be intense. If there is any opportune moment for Oumuamua to reveal its true nature, this period represents it. Active comets rapidly shed their surface layers, exposing underlying material. Any concealed structures or technological components would become more apparent as the obscuring layers of ice and dust ablate. The data acquired by JUICE will not be immediately accessible. ESA has indicated that JUICE is currently on the far side of the Sun relative to Earth, utilizing its high-gain antenna as a heat shield. Communication is being maintained through a smaller, medium-gain antenna, resulting in reduced data transmission rates. The complete dataset from the November observations may not be downloaded and processed until February of 2026. This timeline, several months hence, nonetheless holds the potential for definitive findings. Furthermore, coordination is under consideration between JUICE and NASA's Europa Clipper mission. Both spacecraft are equipped with ultraviolet spectrographs, instruments capable of detecting atoms and molecules by their ultraviolet emissions. If both spacecraft observe Oumuamua simultaneously from distinct vantage points, they could triangulate the spatial distribution of gases within the coma, thereby generating a three-dimensional map of the outgassing process. Such a level of detail has never been achieved for an interstellar object. Now, allow me to address the question that is likely on everyone's mind. Should we attempt to establish communication with Oumuamua? Should we transmit a signal, a message, in an effort to make contact, assuming it is indeed artificial? Avi Loeb has articulated his thoughts on this dilemma. He highlights two primary risks associated with transmitting a message. Firstly, we lack knowledge regarding the capabilities or intentions of any potential recipients. If Oumuamua is a probe dispatched by an advanced civilization, that civilization might perceive an unsolicited message as a threat. Within the framework of the dark forest hypothesis, self-disclosure carries inherent danger. Broadcasting a signal stating, "Here we are intelligent, we exist," could be interpreted as a challenge or a declaration of hostility, potentially eliciting a violent response. Secondly, even if intentions are benign, communication could be subject to misinterpretation. Our message might convey unintended meanings. Language, even in its mathematical or pictorial forms, is fundamentally rooted in context and assumptions. An alien intelligence possessing a vastly different evolutionary history, distinct sensory modalities, and divergent cognitive structures might misunderstand our intended message. A friendly greeting could be perceived as an insult. An offer of cooperation might be interpreted as a sign of subservience. Conversely, if Oumuamua is a probe specifically designed to detect intelligent life, it may be awaiting a response from us. The wow signal, if indeed it originated from Oumuamua, could have been an invitation, a test to ascertain if anyone was listening. By failing to respond, we might be forfeiting an opportunity for contact, for learning, and for accessing knowledge far beyond our current comprehension. Loeb suggests that prior to transmitting any message, we should prioritize observation, treating the situation akin to a blind date. We should observe the other party, endeavor to comprehend their behavior, characteristics, and intentions before initiating dialogue. If Oumuamua maneuvers in ways that suggest intelligence, if it exhibits signs of responsiveness to observation, or if it undertakes any action that indicates awareness of our presence, then we may cautiously consider communication. Rushing to transmit a message without a full grasp of the situation is incredibly imprudent. The Arecibo transmission, dispatched in 1974 towards the globular cluster Messier 13, posed minimal risk. This celestial grouping resides 22,000 light-years away. Even if an entity were to intercept and reply, the journey back and forth would span 44,000 years, rendering any civilization that distant a non-threat on human timescales. However, 3I Atlas is here, within our own solar system. Should it possess the capacity to receive and respond, that reply could materialize within mere months. This drastically alters the risk assessment. We must contemplate our actions with utmost care and consider their potential ramifications. Another scenario merits consideration. What if we are not the first to encounter such a phenomenon? What if 3i Atlas has been in communication with something else already within our solar system? What if other probes, earlier arrivals undetected by us, are coordinating amongst themselves? The WOW signal might not have been aimed at Earth at all, but rather at another recipient somewhere within the solar system. We might have inadvertently intercepted a broadcast never intended for our ears, akin to overhearing a conversation in a language we barely comprehend. If this hypothesis holds true, the pertinent question shifts from whether to communicate to whether to disclose our interception of the message. Perhaps the wisest course of action would be to remain silent, to observe, to gather as much knowledge as possible without announcing our presence. The Galileo project is scheduled to commence its skyward surveillance following October 29th. Loeb has indicated that the project will monitor for heightened activity of unidentified anomalous phenomena subsequent to the object's perihelion passage. If 3i Atlas is indeed a mothership deploying smaller craft, these probes could become detectable as they enter Earth's atmosphere or navigate in proximity to our planet. The observatories employed by the Galileo project are specifically engineered to identify and track such objects. Mere detection would be an unprecedented event. Confirming the existence of extraterrestrial technology within our solar system would represent the most profound discovery in human history. It would resolve the age-old question of whether we are alone. It would serve as irrefutable proof that intelligent life exists beyond our world, that such life is capable of traversing interstellar distances, and that it harbors an interest in our solar system for reasons we can only surmise. Yet, detection is merely the initial step. Following detection arises the critical question of response. Should we endeavor to intercept? Should we attempt to establish communication? Should we prepare defensive measures? Should the public be informed, or should this remain classified information? These are decisions that transcend the purview of any single individual or even a singular government. They necessitate global cooperation, incorporating insights from scientists, ethicists, military strategists, philosophers, and representatives from all of humankind. The fundamental challenge lies in our lack of an established framework to address such a monumental event. There exists no international body vested with the authority to dictate humanity's response to alien contact. While the United Nations possesses a committee dedicated to the peaceful uses of outer space, its mandate is confined to treaties concerning satellites and space stations, not protocols for encounters with extraterrestrial intelligence. SETI, the search for extraterrestrial intelligence, has put forth guidelines for dealing with the detection of an extraterrestrial signal. However, these guidelines presuppose detection via radio telescopes, not the presence of a physical object within our solar system. We are, in essence, ill-prepared. This lack of readiness implies that should an event unfold, the response would be characterized by chaos, fragmentation, and reaction rather than deliberate planning. Individual nations might pursue disparate strategies. Some might advocate for communication, others for concealment, and still others for a confrontational approach. The repercussions could manifest as widespread confusion, missed opportunities, or an escalation of tensions beyond our capacity to manage. Loeb posits that we require an organized entity, an international consortium tasked with the surveillance of interstellar objects and the development of corresponding response protocols. This organization would be responsible for evaluating each object on a defined scale, thereby determining the degree of concern and the appropriate course of action. Objects classified as low concern, unequivocally natural, would necessitate no special measures beyond routine scientific observation. Objects designated as high concern, confirmed as technological and potentially posing a threat, would warrant a coordinated response, potentially encompassing interception, communication, or defensive preparations. The Vera C. Rubin Observatory, slated for full operational status in the near future, is projected to identify interstellar objects at an unprecedented rate. Currently, we detect perhaps one such object every few years. With Rubin, we anticipate discovering dozens annually, possibly even hundreds. Each discovery will demand meticulous assessment. Each could represent the visitor that fundamentally alters our world. Establishing a comprehensive framework in advance of the next significant discovery is paramount. Consider the potential developments within the coming months. If 3i Atlas proves to be a natural phenomenon, we will gain invaluable knowledge about ancient comets originating from distant star systems, thereby broadening our understanding of planetary system formation and evolution, and refining our detection methodologies for future interstellar visitors. This alone would be a significant accomplishment. Conversely, if 3i Atlas is technological in nature, we will have definitive proof that we are not solitary beings in the universe, that advanced civilizations exist, that they are actively exploring the galaxy, and that they have ventured into our solar system. This revelation would fundamentally reshape every facet of human civilization: religion, philosophy, politics, and science would all undergo profound transformation upon the realization that we share the cosmos with other intelligences. The stakes could not be higher, and time is of the essence. And so, here we stand. As September transitions into October, our gaze fixed upon the heavens, awaiting answers that may arrive in days, weeks, or months. 3i Atlas continues its inward trajectory, carrying with it questions we have never been compelled to confront with such gravity. Is it a messenger from another realm? Is it a scout? Is it merely an ancient wanderer, a frozen relic offering a testament to the universe's unfathomable strangeness? The beauty of this present moment, what makes it bearable amidst the pervasive uncertainty, is our collective witness to it. Every telescope trained on that moving speck of light, every scientist meticulously analyzing the incoming data, every individual listening to these words and contemplating their meaning. We are all integral parts of the same unfolding narrative. A narrative centered on our innate curiosity, on our persistent drive to explore beyond the confines of our known world, on our courage to pose questions even when the answers might inspire profound apprehension. I recall Jerry Emmon in 1977 poring over a printout, encountering numerical data that defied conventional explanation, and exclaiming, "Wow," in indelible red ink, for what other single word could encapsulate such an astonishing discovery? He remained unaware of the true significance of his finding. 48 years later, we may finally be on the cusp of understanding. That signal, perhaps, was not an unsolvable enigma. It might have been a salutation, a gesture of goodwill extended across the vast expanse of the void by something already en route. Whether 3i Atlas is a celestial body or an artificial construct, whether it delivers profound knowledge, poses an imminent threat, or simply passes through, leaving us in a state of perpetual wonder, it has already bestowed upon us something of immense value. It has served as a poignant reminder of our cosmic insignificance, our nascent stage of development, and the vast expanse of our ignorance. It has impressed upon us that the universe operates independently of our preconceived notions, our theoretical models, and our comforting certainties. It simply exists, immense, enigmatic, and teeming with phenomena that we have only begun to fathom. The ensuing weeks promise a wealth of data, imagery from Mars, observations as the object makes its closest approach to the sun, and then the anxious wait as it disappears behind the solar disk. We will hold our breath, hoping for its reappearance at the expected location, behaving as predicted, or perhaps, hoping for the unexpected, that it reveals itself more fully, confirming our non-solitary status in the universe. Regardless of the outcome, we will gain knowledge. And it is this pursuit of understanding, this drive to comprehend despite fear and uncertainty, that defines our humanity. It is this same drive that compels us to construct telescopes, to dispatch probes across the solar system, to labor late into the night analyzing data, and to pose questions that lack facile solutions. Thank you for dedicating these hours to delving into this profound mystery, to sitting with the inherent discomfort of the unknown. If you have found value in this exploration, if it has prompted contemplation, sparked wonder, or altered your perspective on the night sky, I would be deeply appreciative if you would like this video and subscribe. This action helps more individuals discover these compelling narratives. And at this juncture, this particular story holds immense significance. It may well be the most important account any of us will ever encounter. Before I conclude, a standard reminder. All information presented herein is derived from peer-reviewed scientific publications, official observational data, and public pronouncements. I have endeavored to present a spectrum of perspectives, from those who perceive evidence of advanced technology to those who advocate for naturalistic explanations. My intention is not to persuade you toward a singular conclusion, but rather to illuminate the fundamental questions and equip you with the information necessary for independent critical thinking. I am not asserting any definitive knowledge regarding the nature of 3i Atlas. No one, in fact, possesses such certainty. We are all collectively awaiting the same answers. The universe is replete with enigmas. Some inspire awe, some evoke dread, and some, like 3i Atlas, may embody both. As October progresses and data streams in, as we observe, anticipate, and ponder, let us remember that we are privileged to be witnesses to something extraordinary. A moment where the veil of ignorance may be drawn back, a moment when everything we understand could be irrevocably transformed. Continue to gaze upward, maintain your curiosity, and regardless of your location or the time of day as you absorb these words, know that somewhere above you, traversing the darkness at a velocity of 60 kilometers per second, an object originating from another star system is approaching its rendezvous with our sun. The subsequent unfolding of events will be discovered collectively. Good night.